extraordinary patience for the moment when someone curious enough, brave enough, and equipped enough would finally come looking. That moment has arrived, and what has been found will change everything you thought you knew about the frozen edges of our world. We live on a planet that is still, in so many ways, deeply unknown to us. We have mapped the surface of the moon with greater precision than we have mapped the floors of our own oceans. We have sent probes to the outer reaches of the solar system, past planets so distant they appear as nothing more than faint smudges of light, and yet vast stretches of our own polar regions remain unexplored, unmapped, and utterly mysterious. The ice that covers the poles is not simply frozen water. It is a library. It is a time capsule. It is a living, breathing, shifting archive of everything this planet has ever experienced, every volcanic eruption, every ancient climate shift, every organism that ever drifted through an ancient sea or walked across a frozen plain. And when we begin to look carefully at that archive, what we find is nothing short of extraordinary. This is a documentary about ice, but it is not just about ice. It is about the creatures that live beneath it and within it. It is about the sounds that drift through frozen waters and have baffled scientists for decades. It is about the mountains that look like pyramids and the falls that run with what appears to be blood. It is about ancient men found perfectly preserved in glaciers, wolf pups frozen so completely that their fur and whiskers remain intact after 57,000 years, and viruses so old they were ancient before the first human civilization rose from the banks of a river. It is about may or may not exist in ancient rock faces in Alaska, about creatures described by indigenous peoples for generations, about facilities built in remote frozen wilderness that have inspired more theories and speculation than almost any other installation on Earth. And it is about the robots, extraordinary purpose-built machines of science, that have been sent into the dark, icy depths where no human could survive, and have returned with images and data that have left the scientific community breathless. We will travel in the course of this documentary to the most remote and extreme environments our planet has to offer. We will go to the bottom of the world and to the top of it. We will go beneath ice shelves that are larger than entire nations. We will go into waters so cold that a human being would lose consciousness within minutes of exposure. We will go into the past, deep into the past, through the evidence locked within layers of ancient ice and the bodies of creatures that have no business being as well preserved as they are. And we will come back with answers. Not all the answers, no honest documentary about science and mystery can promise that, but enough answers to satisfy, and enough remaining questions to keep the wonder alive. Because that is the thing about these frozen places. The more you learn about them, the more mysterious they become. Every answer reveals 3 new questions. Every discovery points toward a deeper layer of the unknown. The ice gives up its secrets reluctantly, one frozen layer at a time, and each revelation arrives with a sense of profound humility, a reminder that the Earth is vast and ancient and complex in ways that dwarf our imagination. So let us begin. Let us go to the ice. Let us start with what has captured the imagination of millions of people around the world. The viral images, the breathless headlines, the social media posts that spread faster than any scientific paper ever could, the claims that something extraordinary, something perhaps inexplicable or even ancient and artificial, has been found in the ice. Doorways, pyramids, sunken ships. Structures that look like they were built by human hands in places where no human civilization has any business having existed. If you have spent any time on the internet in the past decade, you have almost certainly encountered these claims. A photograph of Antarctica taken from above, showing what appears unmistakably to be a pyramid, a perfect 4-sided geometric form rising from the snow, as precise and deliberate in its angles as anything you might find in Egypt. The image circulates. The comments multiply. Was this built by an ancient civilization? Does it prove that Antarctica was once inhabited? Is this evidence of a lost world preserved beneath the ice waiting to be discovered? The excitement is real, and it is entirely understandable because the image is genuinely striking. But here is the truth, and the truth, it turns out, is nearly as fascinating as the myth. Those pyramidal structures in Antarctica are real formations. They exist. You can photograph them and they will look, especially from certain angles and in certain lighting conditions, exactly like man-made pyramids. But they are not man-made. They are the result of a geological process called differential erosion, a process that has been shaping mountains in frozen environments for millions of years. Here's how it works. When a mountain is surrounded by glaciers, those glaciers act like slow, grinding tools, carving away at the rock from multiple directions simultaneously. Over vast spans of time, we are talking millions of years, this process can sculpt a mountain into a shape with multiple flat angled faces meeting at a central peak. Geologists have a specific term for this formation. They call it a horn, and the most famous example of a horn in the world is the Matterhorn in the Alps, a mountain so perfectly sculpted by glacial action that it looks, from certain angles, almost impossibly precise. The Antarctic formations that look like pyramids are horns. They are geological masterpieces created by the patient, grinding work of ice over geological timescales. They are real, they are remarkable, and they are entirely natural. This distinction matters enormously, not because we want to diminish anyone's sense of wonder, but because the truth is, if anything, more wondrous than the myth. A civilization that built pyramids in Antarctica would be extraordinary. But a geological process that can, over millions of years, sculpt a mountain into a shape indistinguishable from a human-built pyramid, that speaks to something even deeper, to the profound creative power of natural forces operating over timescales that utterly dwarf anything in human history. The mountain was being shaped before the first hominid ever stood upright on the plains of Africa. The ice was carving those faces before our species even existed. That is not less remarkable than an ancient civilization. That is more remarkable than almost anything we can imagine. The same principle applies to many of the other mysterious formations that appear in aerial and satellite photographs of polar regions. What looks like a doorway in a cliff face is most often a natural opening created by the differential weathering of rock. Some types of rock erode faster than others, and the result can be an opening that, especially when photographed from a particular angle or in low light, appears to have been deliberately shaped. What looks like the hull of a sunken ship, glimpsed through ice or in aerial imagery, is typically a rock formation, a ridge, or a shadow cast by the complex topography of a glaciated landscape. This is not to say that every strange formation has an immediate, obvious natural explanation. Sometimes the explanation takes time to find. Sometimes geologists need to travel to a site, examine it directly, take samples, and run analyses before they can say with confidence what they are looking at. But in the vast majority of cases, the explanation, when found, is natural and often more interesting than the supernatural alternative would have been. The doorway claim that forms part of the title of this exploration, a 220-year-old doorway found in Alaska, is a perfect example of this dynamic. The number itself is striking, not thousands of years old, which would suggest a pre-Columbian civilization, not millions of years old, which would be purely geological, 220 years. That specificity lends the claim a kind of false precision that makes it feel more credible than a vague claim of ancient origins. 220 years suggests that someone has done the math, run the analysis, dated the formation. It suggests science. But the reality of what was found, and what it tells us about the history of human presence in Alaska and the natural forces that shape stone and ice in extreme environments, is, as we will discover, genuinely fascinating in its own right. Alaska is a land of extraordinary extremes. It is a land where the landscape shifts from dense boreal forest to open tundra, to glaciated peaks, to volcanic islands within spans of distance that would feel modest anywhere else on Earth. It is a land where the permafrost, the layer of permanently frozen ground that underlies much of the terrain, preserves things with a fidelity that no other environment on Earth can match. And it is a land with a human history that stretches back at least 14,000 years, and possibly much longer, encompassing cultures of extraordinary sophistication and resilience that developed over millennia in one of the most challenging environments our species has ever inhabited. The notion of a doorway in Alaska, of a passage or opening in ancient stone or ice that might mark the site of something significant, resonates so powerfully because it touches on deep questions about who was here before the historical record begins, and what they built, and what traces of their presence might still survive in the frozen ground. These are legitimate questions. These are questions that archaeologists and anthropologists and geologists are actively working to answer. And the answers, as we will see, are remarkable. But first, let us linger a little longer in Antarctica, because no exploration of the world's frozen mysteries can skip past the most extraordinary piece of frozen real estate on the planet. A continent roughly 1.5 times the size of the contiguous landmass that stretches from the Atlantic to the Pacific in the northern hemisphere, covered in ice up to nearly 3 miles thick in places. And hiding beneath that ice a landscape of mountains and valleys and lakes and geological wonders that we are only now beginning to map and understand. Antarctica was not always frozen. This is perhaps the single most important thing to understand about the continent if you want to grasp the full scope of its mysteries. There was a time, a very long time ago, but a time nonetheless, when Antarctica was green, when it had forests and rivers and almost certainly wildlife. When it was attached to the southern edge of a vast supercontinent and enjoyed a climate that, while cool, was far more hospitable than what exists there today. The evidence for this ancient green Antarctica is preserved in the rock, fossils of ferns, of trees, of creatures that required warmth and liquid water to survive have been found in Antarctic rocks, reminders that the white, frozen desert we see today is not the only form this continent has ever taken. The freezing of Antarctica, the process by which it became the ice-covered world it is today, was a gradual process that unfolded over millions of years, driven by the slow movement of tectonic plates and changes in ocean circulation that cut Antarctica off from the warming influence of currents flowing from the tropics. As the continent drifted southward and became increasingly isolated, temperatures dropped, snow began to accumulate, and over millions of years that snow compressed under its own weight into ice, first in the mountains, then spreading outward across the plains and coasts until the entire continent was buried under a sheet of ice so massive that it actually presses the underlying rock downward under its own weight. That ice sheet is, as mentioned, a library. Each year's snowfall adds a new layer, and that layer preserves within it a record of the atmospheric conditions at the time of its deposition. Bubbles of ancient air trapped in the ice, particle dust and ash from distant volcanic eruptions, chemical signatures that tell us about the temperature and composition of the atmosphere at specific moments in geological history. Scientists drill down through these layers, sometimes drilling for miles into the ice, and extract cores that allow them to read this record in extraordinary detail. From ice cores, we know about climate cycles that operated over hundreds of thousands of years before any human being walked the earth. We know about volcanic eruptions that happened on the other side of the planet from a puff of ash preserved in a layer of ice laid down at the same moment in time. We know about changes in the concentration of greenhouse gases in the atmosphere that happened long before humans began burning fossil fuels, changes that help us understand the natural rhythms of the climate system and contextualize what is happening to that system today. The oldest ice cores so far extracted have allowed scientists to peer back approximately 800,000 years into the climate record. But there is ice in Antarctica that may be far older, perhaps more than 1 million years old, and teams of scientists have been working to identify locations where this ancient ice might be accessible for drilling. Each new core represents not just scientific data, but a kind of miracle, a physical sample of the ancient atmosphere, preserved with extraordinary fidelity through an accident of geography and climate, waiting through the rise and fall of entire species for someone to come along and read it. This is the context in which we must understand the strange and wonderful things that scientists have been finding in and around Antarctica in recent decades. The continent is not just a frozen desert. It is an active scientific frontier, yielding discoveries at a pace that has accelerated dramatically as our technology has improved. and some of those discoveries are genuinely astonishing. Consider what lies beneath the ice. Not the geological record, though that is remarkable enough, but the liquid water. The ice sheet of Antarctica is so thick and so heavy that it insulates the rock beneath it, and the combination of geothermal heat rising from below and the insulating weight of the ice above creates conditions deep beneath the surface where liquid water exists. Lakes of liquid water, sealed off from the outside world by miles of ice, untouched by sunlight or atmosphere, isolated from the rest of the biosphere for anywhere from 15 million to 35 million years. The largest of these subglacial lakes is Lake Vostok, named for the Russian research station that sits above it on the surface of the ice. Lake Vostok is not a small lake. It is roughly the size of Lake Ontario, one of the largest freshwater lakes in the northern hemisphere. It has been sealed beneath the ice for at least 15 million years. Some estimates suggest as long as 35 million years. And the question that has consumed scientists since the lake was discovered in the 1990s is, what is alive in there? Because the presumption, and it is a presumption backed by an enormous body of evidence from other extreme environments, is that something is alive in Lake Vostok. Life, as we have learned over the past several decades, is extraordinarily resilient. It turns up in environments that we would have considered completely inhospitable just a few generations ago. Deep-sea hydrothermal vents where water temperatures can reach hundreds of degrees and the pressure is crushing. Highly acidic hot springs, the cores of nuclear reactors, the driest places on Earth where almost no liquid water ever falls, and as it turns out, beneath miles of Antarctic ice. Scientists have been carefully, painstakingly drilling through the ice above Lake Vostok for years, working to access the lake without contaminating it, because contaminating this pristine, isolated environment with organisms from the outside world would destroy the very thing that makes it scientifically valuable. The technical challenges are immense. The drilling itself must be done with extraordinary precision at depths that make the process enormously difficult and expensive. And the question of how to access the lake in a way that is truly sterile, that does not introduce any organisms from the surface, is one that has occupied some of the finest engineering minds working in polar science. What scientists have found in the ice layers immediately above the lake, layers that have been in contact with the lake's water through a process of freezing at the ice-water interface, includes tantalizing evidence of microbial life. Genetic material that suggests organisms adapted to cold, dark, high-pressure conditions. The implication is that Lake Vostok is not sterile, it is not dead. Something is living in that ancient, isolated darkness, doing whatever it is that life does when it has had 15 million years of complete isolation to figure out its own particular approach to existence. What that something is, whether it is recognizably related to surface life, or whether it has diverged so significantly during its long isolation that it represents something genuinely novel, remains an open question. And it is one of the most exciting open questions in all of biology, because the answer will tell us something profound about the resilience of life, about the conditions under which living systems can persist, and by extension, about the possibility of life in other extreme environments elsewhere in the cosmos. Lake Vostok is not unique. Beneath the Antarctic ice sheet, scientists have now identified more than 400 subglacial lakes, a network of isolated water bodies connected, in some cases, by subglacial rivers and streams that flow through the crushing dark beneath miles of ice. Each of these lakes is potentially a separate experiment in the evolution of isolated life. Each is a sealed biosphere, a world within a world, carrying whatever lived in it at the time the ice sealed it off from the surface, and whatever that original life has evolved into over the intervening millions of years. The scale of this hidden hydrological network is, once you grasp it fully, almost impossible to process. Beneath the ice of Antarctica, beneath the white, apparently featureless expanse that most people picture when they think of the continent, there is a dynamic, flowing system of water that has been operating for millions of years, hidden from the sun and from everything that depends on the sun for energy, running on nothing but geothermal heat and the strange, persistent chemistry of life in the dark. But what about life in the ocean around Antarctica? What about the waters that surround the continent, the Southern Ocean, one of the most productive and biologically rich marine environments on Earth despite its extraordinary cold? This is where the robots come in, and this is where some of the most genuinely astonishing discoveries of recent years have been made. Oceanographers and marine biologists have developed over the past 2 decades a suite of extraordinary robotic tools for exploring environments that are inaccessible to humans. Autonomous underwater vehicles, AUVs, that can be programmed to follow a specific path, diving to specified depths, collecting data along the way, and then returning to the surface to be retrieved. Remotely operated vehicles, ROVs, that are tethered to a ship by a cable and can be piloted in real time by operators watching through the vehicle's cameras, descending into environments where no human could survive to collect samples, take photographs, and make observations that would otherwise be impossible. 2 of these vehicles have been particularly important in the exploration of Antarctic waters and the underside of Antarctic ice shelves. The first is an AUV called RAN. RAN was developed at the University of Gothenburg in Sweden and is named for a Norse goddess of the sea. It is a torpedo-shaped vehicle, roughly 4 meters long, capable of operating independently for extended periods and navigating through environments that would be extraordinarily challenging for a human-operated vehicle, including beneath the floating ice shelves that extend from the edges of the Antarctic ice sheet out over the ocean. The ice shelves of Antarctica are among the most important and least understood features of the continent's glaciological system. They are enormous floating platforms of ice, some of them larger than entire nations, that form at the edges of the continental ice sheet where glaciers flow out to the sea and begin to float. The largest of them, the Ross Ice Shelf, covers an area larger than many of the world's small countries, and it is several hundred meters thick. The undersides of these shelves, the surfaces that are in contact with the ocean water beneath them, have been almost entirely inaccessible to scientific investigation until the development of vehicles like RAN. RAN has been deployed beneath the Thwaites Glacier, one of the most closely watched glaciers in Antarctica, a glacier of extraordinary size and significance that has been the subject of intense scientific scrutiny because of what its potential behavior in a warming climate might mean for sea levels around the world. To get RAN beneath the Thwaites Glacier, scientists drilled a hole through several hundred meters of ice, lowered the vehicle through the hole, and then watched as it disappeared into the dark water beneath the ice shelf and navigated autonomously through an environment that no human has ever entered, and perhaps no human ever will. The data that RAN brought back from beneath the Thwaites Glacier has been scientifically invaluable: detailed maps of the underside of the ice shelf, measurements of the temperature and salinity of the water beneath it, information about the ocean currents that are driving warm water against the base of the glacier and melting it from below. This is critical information for understanding one of the most consequential geological and glaciological processes currently underway on Earth. But the data about the physical state of the glacier, as important as it is not the only thing that robotic explorers have found beneath Antarctic ice. The second robot of note is an ROV called Subglacial, operated by the Schmidt Ocean Institute, and it has been deployed in the open waters around Antarctica as well as in other extreme marine environments around the world. Subglacial is a different kind of tool than RAN. It is tethered, controlled in real time by human operators aboard a ship, equipped with cameras, lights, and robotic arms capable of collecting samples and manipulating objects in the environment. And what Subglacial and its operators have found in Antarctic waters has been, in the strictest sense of the word, astonishing. Scientists had long assumed that the deep waters beneath Antarctic ice shelves waters that receive no sunlight, that are frigidly cold, and that are in many cases sealed off from open ocean currents by the overhanging mass of the ice shelf above, would be largely lifeless, or at most sparsely inhabited by a few specialized organisms adapted to the extreme conditions. The logic seemed sound. Without sunlight, there is no photosynthesis. Without photosynthesis, there is no energy entering the system through the standard pathway that sustains most of the world's ecosystems. And without energy, the argument went, complex ecosystems could not develop. The logic was wrong. What Sebastian found beneath Antarctic ice shelves was not a barren, lifeless void. It was a thriving, complex, surprisingly rich ecosystem populated by organisms that have found ways to exist and even flourish in the absence of sunlight, in waters that hover just above freezing, in the dark and crushing silence beneath hundreds of meters of ice. Corals, sponges, sea spiders, sea worms of varieties previously unknown to science, crustaceans. Filter feeders of astonishing complexity and variety, anchored to rock surfaces and reaching up into the water column to capture whatever organic particles drift past. The images that came back from these dives were, for many in the marine biology community, almost literally unbelievable. Here were complex communities of organisms, communities that would not have looked entirely out of place in a temperate ocean, in terms of their structural complexity and species diversity, existing in conditions that everything we thought we knew about ecology suggested should not support them. How is this possible? The answer involves some fascinating and relatively recently discovered mechanisms of energy input into deep, dark ocean systems. In some cases, organic material, the bodies of dead organisms, the remains of creatures that lived near the surface of the ocean, sinks through the water column and reaches the deep floor, providing a slow rain of organic matter that sustains communities of filter feeders and decomposers. In other cases, chemosynthesis, the process by which certain bacteria derive energy from chemical reactions rather than from sunlight, provides the foundation for food webs that operate entirely independently of solar energy. And in some cases, the specific geography of the Antarctic ice shelves creates conditions where water currents bring nutrients into otherwise isolated environments in ways that scientists are still working to understand fully. The discovery of these thriving ecosystems beneath Antarctic ice shelves has implications that extend far beyond Antarctic science. It speaks to the fundamental resilience of life, to life's apparently inexhaustible capacity to find ways to exist, to metabolize, to reproduce, to build complex communities in environments that seem from the outside to be completely unsuitable. And it has direct implications for the search for life in other parts of the solar system, particularly for bodies like Europa, a moon of Jupiter, or Enceladus, a moon of Saturn, both of which are believed to harbor liquid water oceans beneath thick shells of ice, warmed by tidal heating rather than solar energy. If life can thrive beneath the ice shelves of Antarctica, the argument goes, then why not beneath the ice shell of Europa? Why not in the subsurface ocean of Enceladus? This is not science fiction. These are active areas of astrobiological research, informed directly by what scientists are learning from the exploration of extreme environments on Earth. And Antarctica, cold, dark, frozen, remote Antarctica, is providing some of the most important data points in this emerging field. Among the creatures documented by robotic exploration of Antarctic waters, few have captured the public imagination as completely as the giant phantom jelly. This organism, formerly known as Stygiomjusa gigantea, is one of the largest invertebrates in the ocean, a medusa or jellyfish that can grow to enormous size, with a bell that may exceed a meter in diameter and trailing oral arms that can extend to 10 meters in length. It is a creature of the deep ocean, rarely seen, seldom photographed, and until relatively recently, known primarily from specimens that had been accidentally captured in nets and from the occasional fleeting encounter reported by deep-sea researchers. The giant phantom jelly is not exclusively Antarctic. It has been observed in deep waters in multiple ocean basins around the world, but it is in Antarctic and subantarctic waters that some of the most significant observations have been made. When footage of a giant phantom jelly drifting through the darkness of the deep ocean is first encountered, the reaction is almost universally one of arrested attention. There is something about this creature, its immense, slow grace, the ghostly translucence of its bell, the way its long arms trail behind it in the current like the robes of some deep ocean deity, that is both deeply alien and strangely compelling. The giant phantom jelly is, like so much of the deep ocean fauna that has been documented in recent years, a reminder that the ocean conceals worlds of biological complexity and variety that we have barely begun to explore. The deep sea, everything below about 200 meters, where sunlight no longer penetrates, covers more than half the surface of the planet. It is the single largest habitat on Earth, and it is, in terms of systematic biological survey, the least explored. The vast majority of the species that live there have not been described by science. Many of them have never been seen by human eyes. The deep ocean is, in a very real sense, the last great unexplored frontier on this planet. Antarctic waters are particularly rich in deep-sea diversity, in part because of the unique oceanographic conditions of the Southern Ocean. The Antarctic Circumpolar Current, the mightiest ocean current on Earth, driven by the unimpeded winds of the southern latitudes and flowing continuously around the continent, generates a complex pattern of water circulation that brings nutrient-rich water up from the depths to the surface and then plunges it back down again. This circulation pattern, known as upwelling and downwelling, creates conditions of extraordinary biological productivity near the surface, the famous Antarctic summer, when vast blooms of phytoplankton and krill support enormous populations of penguins, seals, whales, and seabirds. But it also creates dynamic conditions in the deep water beneath, conditions that support biological communities of remarkable diversity. The organisms that Sebastian and other deep-sea vehicles have documented in Antarctic waters include not just the giant phantom jelly, but an extraordinary range of other species. Some of them familiar, many of them known but poorly understood, and some of them genuinely new to science. Sea spiders, formerly known as pycnogonids, that can grow to enormous size in the cold, oxygen-rich Antarctic waters, a phenomenon known as polar gigantism, in which organisms that would be tiny in warmer, lower oxygen waters reach extraordinary sizes in the Antarctic environment. Corals that grow at depths of hundreds of meters, building intricate three-dimensional structures in the darkness. Sponges that may live for thousands of years, growing slowly and filtering enormous quantities of water through their porous bodies over the course of their extraordinarily long lives. Each of these organisms tells a story. The sponges, with their potential lifespans measured in thousands of years, are among the longest-lived animals on Earth, animals whose lives began before the development of the printing press, before the construction of medieval cathedrals, potentially before the fall of ancient Rome. They have been filtering the waters of the Southern Ocean through their bodies for longer than most human institutions have existed. They are, in their own quiet, sessile way, living time capsules, carrying within their biology a record of the ocean conditions they have experienced over their extraordinary lifespans. The corals of the deep Antarctic Ocean are similarly remarkable. Unlike the warm water corals that build the colorful reef systems of tropical oceans, reef systems that depend on photosynthetic algae living within their tissues for much of their energy, deep water corals are filter feeders, obtaining their energy entirely from the organic particles that drift past them in the current. They build complex calcium carbonate structures, and those structures provide habitat for an enormous diversity of associated organisms. Fish, crustaceans, worms, and many other invertebrates that use the coral framework as shelter, hunting ground, and spawning site. Deepwater coral reefs are, in terms of their ecological function, analogous to the shallow water tropical reefs that are far more familiar to most people, but they exist in conditions of permanent darkness and cold that are about as far from a tropical reef environment as it is possible to get within the ocean. The discovery and documentation of these deep-water coral communities in Antarctic and subantarctic waters has been one of the significant achievements of recent marine biological exploration. It has expanded our understanding of where complex reef ecosystems can exist and has revealed a dimension of ocean biodiversity that was, until recently, almost entirely unknown. Now let us turn to sounds. Because one of the most remarkable and, until recently, most mysterious aspects of the Antarctic Ocean is not what is seen in it, but what is heard. The ocean is not a silent place. It never has been. Long before the era of human-generated noise, the ocean was filled with the sounds of biological life, the songs of whales, the clicks of dolphins, the grinding and snapping of crustaceans, the chorus of fish chorusing at dawn and dusk. But there are sounds in the Antarctic Ocean that have taken scientists years to identify, sounds that were so unfamiliar and so strange when first recorded that they sparked considerable speculation about their origins. The story of mysterious ocean sounds begins, for many people, with the bloop. The bloop is the name given to an extremely powerful, ultra-low frequency underwater sound detected by hydrophones in the southern Pacific Ocean in 1997. The name is informal. It was assigned by the scientists at the agency that detected it, a reflection of the sound's acoustic character, which in speeded-up recordings does indeed sound something like a bloop. The rating with extraordinary pain have been studied are not known to be a permanently frozen layer of soil associated organisms. Fish, crustaceans, worms, and many other invertebrates that use the coral framework as shelter, hunting ground, and spawning site. Deepwater coral reefs are, in terms of their ecological function, analogous to the shallow water tropical reefs that are far more familiar to most people, but they exist in conditions of permanent darkness and cold that are about as far from a tropical reef environment as it is possible to get within the ocean. The discovery and documentation of these deep-water coral communities in Antarctic and subantarctic waters has been one of the significant achievements of recent marine biological exploration. It has expanded our understanding of where complex reef ecosystems can exist and has revealed a dimension of ocean biodiversity that was, until recently, almost entirely unknown. Now let us turn to sounds. Because one of the most remarkable and, until recently, most mysterious aspects of the Antarctic Ocean is not what is seen in it, but what is heard. The ocean is not a silent place. It never has been. Long before the era of human-generated noise, the ocean was filled with the sounds of biological life, the songs of whales, the clicks of dolphins, the grinding and snapping of crustaceans, the chorus of fish chorusing at dawn and dusk. But there are sounds in the Antarctic Ocean that have taken scientists years to identify, sounds that were so unfamiliar and so strange when first recorded that they sparked considerable speculation about their origins. The story of mysterious ocean sounds begins, for many people, with the bloop. The bloop is the name given to an extremely powerful, ultra-low frequency underwater sound detected by hydrophones in the southern Pacific Ocean in 1997. The name is informal. It was assigned by the scientists at the agency that detected it, a reflection of the sound's acoustic character, which in speeded-up recordings does indeed sound something like a bloop. The original sound, however, was not cute or small. It was extraordinarily powerful enough to be detected by hydrophones more than 5,000 kilometers from where it originated. In the hydrophone network that detected it, designed to track ocean sounds across vast distances, the bloop stood out as one of the most powerful sounds ever recorded in that frequency range. The speculation that surrounded the bloop in the years following its detection ranged from the reasonable to the extraordinary. Some scientists suggested it might be biological, the vocalization of an organism of unprecedented size. This suggestion naturally captured the popular imagination. An organism producing a sound that powerful would have to be enormous, larger than any known marine creature, conceivably. The most extreme versions of this speculation invoked the possibility of a truly gigantic unknown organism living in the deep ocean. The fact that the signal had characteristics consistent with a biological origin, it did not sound like a simple, mechanically generated tone, but had the rising and falling quality of an animal vocalization, added fuel to this particular fire. The more measured scientific consensus, which developed over subsequent years, pointed in a very different direction. The location of the Bloop, when triangulated using multiple hydrophone stations, placed it in the vicinity of the southern Pacific Ocean, not far from the Antarctic coast. And the distinctive characteristics of the sound, when compared to data from other types of acoustic events in that region, led scientists to conclude that the most likely origin of the Bloop was a large-scale icequake, a sudden fracturing or shifting of a large mass of ice, releasing energy that propagated through the water as sound. Large icebergs calving from glaciers or breaking apart as they drift through warmer waters can produce enormous amounts of sound, and in some cases that sound has characteristics that, to the untrained ear or in certain recording conditions, can seem to have a biological quality. The Bloop was almost certainly ice, not a monster, not an unknown leviathan lurking in the deep southern ocean. Ice enormous, dramatically breaking, releasing its stored energy in a burst of acoustic power that traveled halfway across the Pacific Ocean. Which is, when you think about it, still remarkable. The fact that a piece of ice breaking apart can produce a sound detectable 5,000 kilometers away is itself a testament to the extraordinary acoustic properties of the ocean and the sheer scale of the forces involved when major Antarctic ice structures break apart. But the Bloop is not the only mysterious sound from Antarctic and sub-Antarctic waters. There is also the Bioduck, a name given to a sound that was detected repeatedly in the Southern Ocean over many years and that stumped scientists for a considerable time. The Bioduck got its name from its resemblance, in recordings, to the sound of a duck, a quacking, rhythmic sound that repeated at regular intervals. It was clearly biological in origin. Its regular rhythmic pattern and its acoustic characteristics pointed unmistakably toward a living source, but for years, no one could identify what organism was producing it. The Bioduck was first detected in recordings made in the Southern Ocean in the 1960s and continued to appear in hydrophone records over subsequent decades. Because it was encountered in the waters around Antarctica and in the approach to Antarctic waters, scientists speculated that the source was some form of Antarctic marine life, perhaps a whale species, perhaps a large fish, perhaps something else entirely. The regularity of the sound, its consistent acoustic properties, and the fact that it appeared seasonally all pointed toward a biological origin, but identifying which specific organism was responsible proved surprisingly difficult. The identification, when it finally came, was deeply satisfying. The Bioduck is produced by Antarctic minke whales, relatively small baleen whales that are abundant in Antarctic waters, and that play an important role in the ecosystem of the Southern Ocean. The identification was made possible by new technology, a combination of acoustic recording equipment deployed on underwater gliders and tagging technology that allowed researchers to attach small acoustic recorders directly to minke whales. When the recordings from these whale-mounted tags were examined, the distinctive Bioduck pattern appeared clearly in association with the tagged animals, definitively linking the sound to the minke whale. The significance of this identification extends beyond the mere satisfaction of solving a long-standing mystery. Once scientists know what animal is producing a sound, the sound itself becomes a tool. Because the Antarctic minke whale is notoriously difficult to observe, it is smaller and less conspicuous than many other whale species, and it frequently travels beneath sea ice where surface observation is impossible. The ability to identify and track its distinctive call using hydrophone networks opens up new possibilities for studying the behavior, population size, and movements of these whales in ways that direct observation alone could never achieve. This is the deeper significance of solving mysteries like the Bioduck. The solution is not just satisfying in itself, it is scientifically useful. And it speaks to the broader principle that the careful, patient, rigorous investigation of mysterious phenomena in extreme environments is not just intellectually rewarding but practically valuable, leading to insights and tools that would not have been possible without the initial mystery and the effort to resolve it. Then there is the Biotwang, a sound that is, if anything, even more evocative in its name and even more bizarre in its character than either the Bloop or the Bioduck. The Biotwang was first described from recordings made in the Pacific Ocean, at depths of several hundred meters. It is a complex sound, a metallic, almost science fiction-like vocalization that has been described as sounding like a sound effect from a science fiction film. It consists of several distinct components: an opening downsweep followed by a series of metallic-sounding pulses, followed by an extended low-frequency moan. The combination is genuinely strange, and recordings of it, when shared with people unfamiliar with ocean acoustics, routinely generate reactions of surprise and disbelief. The Biotwang, like the Bioduck, is biological in origin. It is produced by another whale, specifically the dwarf minke whale, a form that is closely related to the Antarctic minke whale. Whales are found in tropical and subtropical waters of the Pacific and Indian Oceans, and their extraordinary vocalization has been known to researchers who work with this species for some time, though the Biotwang designation and its public profile are more recent. The function of the sound, why dwarf minke whales produce this particular complex vocalization, is not fully understood. It appears to be a social call, potentially associated with mating, but the details of its role in dwarf minke whale communication remain an active area of research. These biological sounds, and the many others that populate the acoustic landscape of the ocean, from the infrasonic rumbles of blue whales to the high-frequency clicks of sperm whales echolocating in the deep, are not just interesting in themselves. They are data. Each vocalization contains information about the animal that produced it, its identity, its location, potentially its behavioral state. And as hydrophone networks become more sophisticated and the analytical tools for processing acoustic data improve, the ocean's soundscape is becoming an increasingly powerful source of biological information, a way of monitoring the living ocean at scales and with continuity that no other method can provide. It would be impossible to discuss the mysteries and wonders of the Antarctic and subantarctic environment without spending time on one of the most visually striking and scientifically interesting features of the entire continent, the Blood Falls. The Blood Falls is, in images, almost literally unbelievable. It is a waterfall, or more precisely, a seep of water that emerges from the snout of the Taylor Glacier in the McMurdo Dry Valleys of East Antarctica, and the water that flows from it is blood red. Not brownish red, not vaguely pinkish, genuinely, vividly, dramatically red, the color of fresh blood, staining the ice and snow around the outlet in a way that makes the location look like something out of a particularly vivid nightmare. The Blood Falls was first described by a geologist named Griffith Taylor in 1911 during one of the early expeditions to Antarctica. Taylor, seeing the red stain on the glacier, initially attributed it to algae, thinking that some form of red pigmented algae was producing the color. This was a reasonable hypothesis at the time, and the valley was subsequently named after him. But the true explanation for the Blood Falls is considerably more interesting than algae. Beneath the Taylor Glacier, sealed off from the outside world by ice and by the extreme conditions of the McMurdo Dry Valleys, there is a reservoir of brine, highly saline water, so salty that it remains liquid at temperatures well below the normal freezing point of water. This brine, which has been sealed beneath the glacier for an estimated 1.5 to 2 million years, is extraordinarily rich in dissolved iron. The iron has accumulated in the brine through geological processes operating over those 2 million years of isolation, the slow dissolution of iron-bearing minerals in the rock beneath the brine, releasing iron ions into the water. When the brine reaches the surface, when it seeps out through the snout of the glacier and is exposed to the oxygen in the atmosphere, the dissolved iron immediately oxidizes, just as iron oxidizes when exposed to oxygen in the everyday world. Oxidized iron is rust. And rust is red. The vivid crimson color of the blood falls is simply iron rusting, but iron rusting in the most dramatic possible circumstances, in quantities sufficient to paint the ice of a glacier the color of blood, emerging from a reservoir that has been isolated from the outside world for 2 million years. But the visual spectacle of the blood falls is not the most remarkable thing about it. The most remarkable thing is what is living in the brine. Because the brine beneath the Taylor Glacier, despite its extraordinary salinity, its sub-zero temperature, its complete isolation from sunlight, and its complete lack of oxygen, is not sterile. It is home to a community of microorganisms, bacteria, that have been surviving in these conditions for approximately 1.5 million years. These bacteria are not just surviving passively, ticking over at minimal metabolic rates and waiting for conditions to improve. They are actively metabolizing, carrying out the complex chemistry of life, using chemical reactions involving sulfur and iron as their energy sources rather than sunlight or oxygen. This is one of the most extreme and most isolated microbial ecosystems ever discovered. The organisms in the blood falls brine have been cut off from the rest of the biosphere for longer than modern humans have existed as a species. They have had nearly 2 million years of isolated existence in which to adapt to their extraordinary environment, and the biochemical strategies they have developed for surviving in that environment are of intense interest to microbiologists and astrobiologists alike. If life can persist for 2 million years in a freezing, airless, intensely saline brine reservoir beneath an Antarctic glacier, then the range of environments elsewhere in the solar system that might support life expands considerably. The blood falls is a reminder that in extreme environments, the appearance of impossibility is not always a reliable guide to what is actually possible. A dark, frozen, airless brine reservoir 2 million years old looks, from the outside, like the last place you would expect to find a thriving community of living organisms. And yet that community has existed for a very long time, and is telling us something profound about the nature of life and the envelope within which it can operate. The McMurdo Dry Valleys, where the blood falls is found, are themselves one of the most extraordinary places on the surface of the earth. They are a small region of Antarctica, small relative to the vast ice-covered expanse of the continent, though still covering an area of several thousand square kilometers, that is, paradoxically, almost entirely free of ice and snow. The valleys are sheltered from the flow of the continental ice sheet by a ring of mountains, and the winds that flow down from those mountains are so dry and so powerful that they sublimate any snow or ice that falls in the valleys before it can accumulate. The result is a landscape that looks, at first glance, almost like a desert in a temperate or even tropical region, rocky, barren, with exposed mineral soils and the occasional lake or frozen river. The dry valleys receive almost no precipitation. The humidity is extraordinarily low. Temperatures are extreme even by Antarctic standards. In winter, they can fall to -30 or -40 degrees Celsius. The ultraviolet radiation that reaches the surface is intense because the atmosphere above Antarctica is thinner than elsewhere on Earth, and because there are times of year when ozone depletion creates conditions of particularly high UV exposure. In short, the dry valleys are about as hostile to life as any environment on the surface of the Earth, and yet life is present in the dry valleys. Not abundant life, not the teeming biological richness of a tropical forest, or even the surprisingly productive marine ecosystem of the surrounding Southern Ocean. but life, persistent, resourceful, extraordinary life that has found ways to eke out a minimal but real existence in conditions that should, by any reasonable assessment, be lethal. The most remarkable of the Dry Valley's organisms are the endolithic bacteria that live not on the surface of rocks but inside them. These organisms have found a way to exploit the fact that certain translucent rocks, particularly rocks like quartz, allow a small amount of sunlight to penetrate a few millimeters into the rock's interior, while the rock itself provides shelter from the desiccating winds, the extreme temperature fluctuations, and the lethal UV radiation of the surface. Just millimeters beneath the surface of certain rocks in the dry valleys, there are communities of bacteria, fungi, and algae that have found a livable environment in a place that is, from the outside, utterly inhospitable. These endolithic communities are slow, their metabolism is minimal, their growth rates are measured in fractions of a millimeter per year. They are, by the standards of most biological systems, almost painfully tentative in their existence, but they are alive. They are carrying out photosynthesis, albeit at extremely low rates. They are reproducing, albeit very slowly. They are persisting in conditions that no other form of multicellular life could tolerate, and they represent one of the most extreme examples of biological resilience ever documented on Earth. The endolithic bacteria of the dry valleys have obvious implications for the search for life on Mars. The surface of Mars, cold, dry, bathed in ultraviolet radiation, with a thin atmosphere that provides almost no protection from cosmic radiation and solar wind, is in many ways not entirely unlike the dry valleys of Antarctica. If organisms can live inside rocks in the dry valleys, surviving conditions that are superficially similar to those on the Martian surface, then perhaps organisms could survive in similar niches on Mars. Perhaps not on the current surface of Mars, which is more extreme than the dry valleys in several important respects, but in rocks, in subsurface environments, in places where liquid water or at least occasional moisture might still exist. These are speculations, to be clear. They are carefully reasoned speculations, grounded in real data and real science, but speculations nonetheless. The evidence for life on Mars remains, at the moment of this documentary's production, exactly zero: no confirmed detection, no unambiguous signature of biological activity, no fossil microbial community preserved in ancient Martian rock. But the logic of the analogy is sound, and the dry valleys of Antarctica, along with the blood falls and the subglacial lakes and the ecosystems beneath the ice shelves, continue to inform and refine our understanding of what life can do when it puts its mind to it. We have spent considerable time in Antarctica, and rightfully so. It is a continent that rewards sustained attention with increasingly astonishing revelations. But the icy world is not limited to the bottom of the planet. The top of the planet, the Arctic and the subarctic regions that surround it, including the vast interior of Alaska, are equally rich in frozen mysteries, and in some ways those mysteries are more immediate, more tangible, and more directly connected to the human story. The Arctic is different from Antarctica in one crucial respect: people live there. People have been living there in some of the most challenging conditions that human societies have ever faced for thousands of years. The indigenous peoples of the Arctic and subarctic, the Inuit, the Yupik, the Athabascan peoples of interior Alaska, the many other groups who have made these frozen landscapes their home, have developed over millennia a depth of knowledge about their environments that is extraordinary by any measure. They know the ice in ways that no visiting scientist, however well equipped, can fully replicate. They have names for conditions of ice and snow and weather that have no equivalents in any other language, because those conditions were important enough, literally important enough for survival, that they needed to be distinguished, described, communicated accurately. This knowledge matters to science. The combination of generations of accumulated indigenous knowledge with modern scientific tools and methods has, in recent years, produced insights that neither could have achieved alone. Indigenous hunters who have been watching wildlife populations across vast areas of Arctic landscape for their entire lives building on the knowledge of their parents and grandparents and great-grandparents, have observations about changes in those populations and in the environment that provide data going back far further than any systematic scientific monitoring program. When indigenous knowledge and scientific data are placed in conversation with each other, the resulting synthesis is far more powerful than either source of information on its own. But the human connection to the frozen world of Alaska and the Arctic extends back not just decades or centuries, but thousands of years, and the evidence for that ancient connection is preserved with extraordinary fidelity in the frozen ground. Permafrost, the permanently frozen layer of soil and rock that underlies enormous areas of Alaska, Canada, Siberia, and other high-latitude regions, is not merely a geological feature. It is a preservation medium of astonishing power. When an organism, an animal, a human being, a plant, is incorporated into permafrost, either by falling into a frozen lake or being buried by sediment and ice or simply dying in a location where permafrost reaches the surface, the freezing process can preserve that organism with a degree of completeness that no other natural process approaches. The quality of permafrost preservation is, to put it simply, miraculous. Not in a supernatural sense, but in the sense that the end results are so complete, so detailed, so far beyond what any other preservation process achieves, that they inspire something very close to awe. We are talking about organisms whose soft tissues, skin, muscle, internal organs, fur, feathers, even the contents of the stomach, are preserved intact. We are talking about preservation that, in some cases, is so complete that the original coloration of the fur or skin is retained, along with the microscopic structure of individual cells. We are talking about biological material that is so well preserved that it is possible, in some cases, to extract intact DNA, not fragmented, degraded genetic material, but sequences long enough to reconstruct significant portions of the genome. The implications of this kind of preservation extend in multiple directions. It allows us to reconstruct the biology of extinct species with a precision that would otherwise be completely impossible. It allows us to understand, through analysis of gut contents and associated plant material, what these animals were eating and what the environment around them looked like at the time of their death. And in the case of ancient viruses, a subject we will return to, it raises profound questions about what else might be preserved in permafrost and what might happen to that preserved material as the permafrost changes. Let us talk about some specific examples. Let us talk about the individuals, animal and human, who have been returned to us by the ice, preserved far beyond their natural lifespan, giving us a window into worlds that we would otherwise know only through stone tools and fossils. The wolf pup that was found in the permafrost of the Yukon region, found in 2016 by gold miners working in permafrost deposits, the kind of discovery that happens with remarkable frequency in areas where gold mining requires the removal and processing of frozen sediment, is one of the most astonishing specimens ever recovered from frozen ground. The pup, subsequently named Zur by the scientists who studied it, was approximately 7 weeks old at the time of its death. It is 57,000 years old, and it is almost perfectly preserved. 57,000 years. This is a number that is almost impossible to internalize. 57,000 years ago, modern humans had not yet reached Australia. The last ice age was building toward its maximum, and vast ice sheets were spreading south from the poles, reshaping the landscapes of the northern hemisphere. The ancestors of today's indigenous Americans had not yet crossed from Siberia to Alaska. The cave paintings of Lascaux and Altamira were still 30 to 40,000 years in the future. The entire recorded history of human civilization, every city, every empire, every written word, every work of art that we can date is contained within the last 10,000 of those 57,000 years. And through all of that time, Zur lay in the frozen ground, perfectly preserved, as the world changed around him in ways beyond imagination. His fur retained its color. His whiskers, delicate, fine whiskers, the kind that a 7-week-old wolf pup would have as it begins to navigate the world through its sensitive nose, were intact. His facial features were clear. He was, in the images taken by the scientists who studied him, recognizably a wolf pup, cute and small and somehow, despite the vast gulf of time that separates his moment of death from our moment of discovery, deeply familiar. The analysis of Zur's remains provided a remarkable amount of information about this individual animal and about the wolf populations of which he was a part. Isotopic analysis of his tissues revealed information about his diet and the environment in which his mother had been living. Genetic analysis, made possible by the exceptional preservation of his DNA, revealed his relationship to other wolf populations, past and present, helping scientists understand the complex evolutionary history of wolves in the Americas and their relationship to the ancestral populations of Siberia and Beringia. Even the analysis of the parasites and microbes associated with his remains provided data about the health of ancient wolf populations and the ecosystem they inhabited. Zur is one example among many. The permafrost of the Yukon and Alaska has yielded an extraordinary array of preserved specimens over the years: horses, bison, mammoths, mastodons, ground sloths, and numerous other species of the Pleistocene megafauna that once roamed these landscapes in abundance before their extinction at the end of the last ice age. Each specimen that emerges from the permafrost is a data point, a piece of the puzzle of understanding what these animals were like, how they lived, and why they disappeared. And occasionally the specimens that emerge are spectacular enough, complete enough, old enough, well-preserved enough to command attention far beyond the scientific community. The discovery of baby woolly mammoths preserved in permafrost has generated particular public interest, and with good reason. Woolly mammoths, the iconic large herbivores of the Pleistocene, whose remains have been found across a broad swath of the northern hemisphere from Europe through Siberia to North America, are known primarily from bones and tusks, from ancient DNA extracted from frozen specimens, and from the remarkable cave paintings and sculptures produced by the humans who lived alongside them. But occasionally the permafrost yields a specimen of far greater completeness, a mummified mammoth, preserved with skin and fur and sometimes even stomach contents intact. The most complete mammoth specimens have been found in Siberia, where the permafrost is particularly deep and ancient, but specimens have also been recovered from Alaska and the Yukon. These animals, when they are found, are not the skeletal remains that most people associate with museum displays. They are the animals themselves, shrunken and desiccated, but recognizably real, their reddish-brown fur matted and compressed but intact, their trunks and ears and feet preserved in sufficient detail to give a genuine sense of what a living, breathing woolly mammoth looked like in a way that no reconstruction from bones alone can fully provide. The stomach contents of permafrost-preserved mammoths are particularly valuable scientifically. Because the food in the stomach was preserved at the moment of death, sealed from the moment the animal died until the moment the permafrost was disturbed and the specimen was exposed, it provides a direct record of what the animal was eating in the last hours of its life. Analysis of those stomach contents reveals the composition of the plant communities of the late Pleistocene landscape: grasses, sedges, flowering plants, mosses, painting a picture of the ancient environment with a specificity that pollen records and other indirect evidence cannot match. These are not just curiosities. They are data, and the data they provide feeds into our understanding of the ecological transformations that accompanied the end of the last ice age, the changes in climate, vegetation, and potentially human hunting pressure that together resulted in the extinction of the woolly mammoth and the other large mammals of the Pleistocene. Understanding that extinction is not just a matter of historical interest. It is directly relevant to the conservation challenges of the present day, where species are disappearing at rates that rival or exceed the extinction rates of past mass extinction events. Among the most remarkable human stories to come out of the frozen world is the story of Ötzi the Iceman, though Ötzi was found not in Alaska or Antarctica, but in the Alps, in a glacier on the border between what is now Italy and Austria. Ötzi's story deserves telling in the context of this documentary because it represents, with particular clarity, the kind of revelations that frozen preservation makes possible, and because it illustrates principles that apply equally to the permafrost mummies of Alaska and the Yukon. Ötzi was found in September 1991 by two hikers who noticed something protruding from the ice in a glacial hollow high in the Alps. At first, the discovery was treated as a routine recovery of a recently deceased mountain victim. Tragically, climbers do occasionally die in the Alps, and their bodies are sometimes preserved by ice for years or decades before being discovered. But as the body was examined more carefully, it became clear that this was no ordinary victim of a recent mountaineering accident. Ötzi was old, not just decades old. He was approximately 5,300 years old, a man who had died in the late Neolithic period, when agriculture was just spreading into Central Europe and the first metal tools were beginning to appear. The preservation of Ötzi's body by the glacier ice was extraordinary. His skin, though mummified and darkened, covered most of his body. His equipment, clothing, tools, weapons, was preserved alongside him, including a copper-bladed axe, a bow and arrows, a knife, and various other implements that spoke of a life lived in intimate relationship with the alpine environment. His clothing was made of a sophisticated combination of materials, goatskin, deer hide, and other animal products, assembled with a skill and knowledge that reflected deep experience with the environment and its resources. The analysis of Ötzi's remains has been going on for more than 3 decades and shows no signs of slowing down. Each new analytical technique that becomes available, and the pace of development of new techniques has been remarkable, reveals new information about this one individual that illuminates aspects of life in the Neolithic Alps that no other evidence could provide. We know that Ötzi was approximately 45 years old at the time of his death. We know that he had calcified arteries, cardiovascular disease, which was unexpected in someone of his era. We know his blood type. We know that he had Lyme disease, having been infected by the bacterium responsible for that condition, making him apparently the oldest known case of Lyme disease on record. And we know how he died. This is perhaps the most dramatic piece of information to come from the analysis of Ötzi's remains. He was murdered. An arrowhead found lodged beneath his left shoulder, in a position suggesting the arrow had been shot from below and behind, an analysis of his right hand showing wounds consistent with defensive injuries sustained in a struggle, combined to paint a picture of a violent end. Ötzi was shot from behind with an arrow, almost certainly while fleeing. He died on a high alpine pass, and the glacier buried him and preserved him so completely that 5,300 years later, we can reconstruct the manner of his death with a clarity that leaves little room for doubt. The story of Ötzi is, in miniature, the story of what frozen preservation can do for our understanding of the human past. It takes a single individual, one person who died on a mountain pass, whose life and death would otherwise have left no trace in the historical record, and makes that person knowable to us across an enormous span of time. And the knowledge is not abstract or statistical, it is specific and human. Ötzi had a diet of wild grains and red deer meat, with some ibex meat and various plant foods. He had tattoos, small marks made by rubbing charcoal into small incisions, located at points on his body that correspond to traditional acupuncture points, though whether the tattoos had a therapeutic purpose or some other significance is unknown. He had the traces of a last meal in his stomach. He had a life, and it was cut short by violence, and the ice remembered all of it. The permafrost of Alaska and the Yukon has not yet yielded a human specimen as complete and as well studied as Ötzi, but the potential is there. The conditions in which Alaskan and Yukon permafrost forms and persists are, in many ways, even more favorable for preservation than the alpine glacial conditions that preserved Ötzi. And as mining operations, construction projects, and the natural processes of permafrost thaw continue to expose ancient layers of frozen ground, the possibility of remarkable human discoveries cannot be discounted. There is another dimension of frozen preservation that is, perhaps, simultaneously the most scientifically fascinating and the most practically significant of all the phenomena we have discussed. It involves not animals or human beings preserved in the ice, but something far smaller and far more biologically potent, ancient viruses. The permafrost of the Arctic and subarctic regions contains organic material of extraordinary antiquity. Not just the bodies of large animals and occasional human beings, but the remains of microorganisms, bacteria, fungi, and, importantly, viruses that were living in those environments when the permafrost first formed, potentially tens of thousands or even hundreds of thousands of years ago. For most of this time, those microorganisms have been frozen, metabolically inactive, suspended in a state of biological stasis, preserved by the cold in a form that is not alive in any active sense but is also not truly dead. The discovery that ancient viruses preserved in permafrost can be revived, that they can be thawed, placed in contact with appropriate host cells, and resume their biological activity was made relatively recently, and it has generated significant scientific interest and discussion. In 2014, French scientists working with permafrost samples from Siberia that were approximately 30,000 years old reported the successful revival of a large virus, a so-called giant virus, belonging to a group called the pithaviruses that had been preserved in the permafrost at that depth. The virus, when placed in contact with amoeba cells, which serve as its natural hosts, was able to infect those cells and reproduce normally. After 30,000 years of frozen dormancy, it was alive. This discovery was striking enough in itself, but subsequent work has extended the timeline considerably. In 2022, the same group of researchers reported the revival of multiple ancient viruses from permafrost samples of varying ages, including specimens from layers estimated to be approximately 48,000 years old. Again, the viruses were able to infect amoeba cells after their revival. Again, they were biologically functional after an almost incomprehensible span of time in frozen dormancy. The viruses that have been successfully revived so far belong to groups that infect amoeba and other single-celled organisms, not humans or other vertebrates. The specific viruses that have been studied are not known to be capable of causing disease in people or animals. But the principle they demonstrate, that viruses can survive in a biologically viable state in permafrost for tens of thousands of years, raises questions about other viruses that might also be preserved in permafrost and might, under some circumstances, be released from their frozen state. This is not a call for panic or alarm. The scientific evidence does not suggest that the permafrost is about to release a wave of devastating ancient pathogens. The conditions necessary for a virus to be thawed, to encounter an appropriate host, and to successfully infect that host are specific and in many ways demanding. But the possibility, the theoretical possibility, that permafrost thaw could release biological material of ancient origin that might have some capacity to interact with modern biological systems is a scientific consideration that deserves careful attention. And here is where the permafrost science connects most directly to one of the most significant environmental processes currently underway. The permafrost of the Arctic and subarctic is thawing. This is not a future possibility or a projection. It is a documented, ongoing process that has been monitored by scientists for decades. As temperatures in the high latitudes rise, the permafrost that has been frozen for thousands of years is beginning to melt. The upper layers are thawing, and as they do, the organic material within them, long frozen plant matter, animal remains, microorganisms, and whatever viral material they contain, is being exposed to the air and to liquid water for the first time in thousands of years. The most immediate consequence of this thawing from a scientific perspective is the release of carbon. The organic matter in permafrost, accumulated over thousands of years of biological productivity, contains enormous amounts of carbon in frozen form. When that organic matter thaws and begins to decompose, the carbon is released into the atmosphere as carbon dioxide and methane, both of which are greenhouse gases. The scale of the carbon stored in permafrost globally is enormous. Estimates suggest that permafrost contains roughly twice as much carbon as is currently in the atmosphere. Even a partial release of that carbon would have significant implications for the global carbon cycle. But the thawing of permafrost also releases other things. It exposes sediments that have been frozen since before the last ice age. It allows access to biological material and to viruses that has been sealed in frozen ground for periods of time that dwarf all of recorded human history. The scientific community is paying close attention to this process, and the study of ancient viruses in permafrost is one small but important part of a much larger effort to understand what the thawing of the frozen north is releasing into the modern world. As we move deeper into the frozen mysteries of the north, past the permafrost and its extraordinary preserved contents, past the subglacial lakes and their ancient microbes, past the whale songs and the iron-red seeps and the rocket-shaped robots in the dark, we arrive at a landscape that has captured human imagination in a very different way. We arrive in Alaska. Specifically, we arrive at those aspects of Alaskan history and culture that have generated the kind of legends and stories and unexplained reports that represent the other face of mystery, not the scientific mystery, which yields to careful investigation, but the cultural and experiential mystery, which is in some ways more complex and more resistant to simple resolution. Alaska is a place of extremes in every sense. Its geography is extreme. It encompasses everything from temperate rainforest to Arctic tundra, from volcanic islands to glaciated mountain ranges, from dense boreal forest to open coastal plain. Its wildlife is extreme. It is home to brown bears of extraordinary size, to moose larger than any other deer in the world, to wolves that still range in significant numbers across vast wilderness areas, to creatures of the sea that rival anything in the tropics for sheer biological spectacle. And its relationship with the unknown, with the unexplained, the reported but unverified, the traditional and the mysterious, is correspondingly rich. The indigenous peoples of Alaska, and there are many distinct peoples, with distinct languages, cultures, and traditions, spanning the enormous geographic extent of the state, have long oral traditions that include accounts of creatures and phenomena that do not fit neatly into the categories of mainstream Western natural history. These traditions deserve to be engaged with seriously, not as curiosities or as material for sensationalized entertainment, but as records of generations of close, careful observation of the natural world by people who depended on that observation for their survival. Among the creatures described in various Alaskan indigenous traditions is the figure often referred to as the Alaskan hairy man, a large, bipedal, hair-covered being that moves through the wilderness and is encountered occasionally by hunters and travelers. This figure appears in multiple indigenous traditions across Alaska, described with enough consistency of general characteristics to suggest that the accounts, however they are ultimately to be explained, are drawing on a common pool of experience or tradition. The hairy man of Alaskan legend is not identical to the Bigfoot or Sasquatch of Pacific Northwest tradition, though the figures share certain broad similarities. The Alaskan versions are generally described as more fearful, more associated with specific environments and ecological contexts, and more deeply embedded in a spiritual and cultural framework that gives their encounters a significance beyond the merely zoological. They are not simply large, unknown animals. They are beings with cultural meaning, associated with specific behaviors, specific encounters, specific protocols for what a person who encounters them should do. Does this mean there is a large, unknown bipedal primate living in the wilderness of Alaska? Almost certainly not in the strict zoological sense. The boreal forests and tundra of Alaska, while vast, have been surveyed extensively by biologists, trappers, hunters, and scientists. A large mammal of the size and description implied by the hairy man accounts would be expected to leave physical evidence, tracks, droppings, remains that has not been found in convincing quantities. The biological argument against the existence of an undiscovered large primate in Alaska is significant. But the question of what the accounts represent, what people are experiencing when they report encounters with the hairy man, and what the tradition means within the cultural framework of the indigenous peoples who carry it, is a different and more interesting question. Human beings in wilderness environments, especially in conditions of poor visibility, fatigue, or psychological stress, can have experiences that are genuinely startling and that are difficult to account for in retrospect. Bears walking briefly on their hind legs can be extraordinarily alarming at close range. Unknown sounds in wilderness at night can trigger deep ancestral fears, and the interpretation of these experiences is filtered through cultural frameworks that give specific form and meaning to what might otherwise be merely confusing. The hairy man traditions of Alaska are, in this reading, genuine cultural responses to real experiences in a genuinely mysterious and sometimes frightening environment. They encode knowledge about how to behave in the wilderness, how to respond to encounters with the unexpected, and how to understand one's relationship to the non-human world. Whether or not the creature described is biologically real is, from this perspective, almost beside the point. Similar considerations apply to other legendary creatures of Alaskan tradition. The Cute and the Kupal, figures from specific Alaskan indigenous traditions, described with particular characteristics and behaviors that reflect the specific ecological and cultural contexts of the people who carry these traditions, are examples of the richness and specificity of indigenous knowledge about the non-human world. They are not generic monsters. They are particular beings associated with particular environments and behaviors, embedded in particular cultural frameworks that give them specific meaning. The respectful engagement with these traditions and the recognition that they represent sophisticated ways of encoding knowledge about the world is one of the most important developments in the relationship between Western science and indigenous knowledge systems over the past several decades. Science does not have to choose between taking indigenous knowledge seriously and maintaining its own standards of evidence and methodology. The two can and should coexist, and the synthesis that results from their careful engagement has repeatedly proven to be more powerful than either alone. Before we close the first part of this journey, we must visit one more place in Alaska, a place that has inspired more speculation, more controversy, and more elaborate theories than perhaps any other facility in the entire state. A place whose very existence in a remote wilderness setting has been taken by some as evidence of purposes far beyond the official explanation. A place called HAARP. HAARP stands for High Frequency Active Auroral Research Program, and it is located near Gakona, a small community in interior Alaska. It is a research facility operated by the University of Alaska Fairbanks, and its primary scientific instrument is a large array of antennas, 180 individual antenna elements spread across approximately 30 acres, that together form a high-power, high-frequency radio transmitter capable of broadcasting radio waves into the upper atmosphere. The legitimate scientific purpose of HAARP is the study of the ionosphere, the upper region of the atmosphere, extending from roughly 60 kilometers to 1,000 kilometers above the Earth's surface, where solar radiation ionizes gas molecules and creates a layer of electrically charged particles. The ionosphere plays an important role in radio communications, affecting how radio waves propagate around the Earth, and understanding its behavior is valuable both for fundamental atmospheric science and for practical applications in communications technology. The HAARP antenna array works by broadcasting radio waves upward into the ionosphere and then studying the effects of that radiation on the charged particles there. The studies are coordinated with ground-based instruments and with satellite observations, and they have produced genuine scientific results, peer-reviewed publications in mainstream scientific journals, presentations at conferences, contributions to the broader field of ionospheric science. This is HAARP as science, but HAARP has another life, an alternative life in the popular imagination that is strikingly different from the institutional reality. The facility has been associated, in various popular accounts, with almost every conceivable form of secret or nefarious activity. It has been accused of being capable of controlling weather, of causing earthquakes, of disrupting communications on a global scale, of affecting human consciousness, and of numerous other things that bear no relationship to the physical capabilities of a radio transmitter operating in the high-frequency range. The fact that the facility is in a remote location, that its antenna array looks impressive and somewhat technical from aerial photographs, and that ionospheric physics is not a subject that most people have detailed knowledge of, has made it a convenient focus for speculation of all kinds. The actual capabilities of HAARP are well documented in the scientific literature, which is publicly available. A high-frequency radio transmitter, however powerful, cannot cause earthquakes. It cannot control weather. It cannot influence human consciousness from a distance. The physics of how radio waves interact with matter, particularly with the very diffuse matter of the ionosphere, which is far less dense than the lower atmosphere, simply do not permit these outcomes. The ionosphere is real, and the effects of high-frequency radio waves on it are real and scientifically interesting, but they are effects of a kind that bear no resemblance to the capabilities attributed to HAARP in popular speculation. This is not to dismiss the importance of scrutiny of large scientific facilities or of the research programs they support. Healthy democratic societies should examine how research is funded, what it produces, and what its broader implications might be. But that scrutiny should be grounded in an understanding of what the technology actually does, based on the physical principles involved and the documented experimental results. HAARP is, in the end, a radio telescope for the ionosphere, a tool for studying a real and scientifically important region of the atmosphere using the established physics of radio waves and charged particles. It is located in Alaska because Alaska provides access to the auroral zone, the region around the magnetic poles where the ionospheric effects that HAARP studies are most pronounced and most interesting. And it is there in the wilderness of interior Alaska, quietly doing science year after year, while the legends and theories about its secret purposes continue to circulate in the digital world that has grown up around it. The ice, the dark water, the frozen ground. The ancient viruses and the billion-year-old bacteria. The wolf pup whose whiskers survived 57,000 years of winter. The blood-red falls fed by iron-rich brine from before the dawn of human civilization. The throbbing, quacking, twanging sounds of whales in the deep southern ocean. The corals and sponges and giant phantom jellies drifting through the darkness beneath miles of ice. The pyramids that are mountains and the doorways that are rocks and the radio transmitter in the Alaskan wilderness. All of it is connected, not by conspiracy or by ancient secrets or by the hidden hand of some unknown civilization. Connected by something both simpler and more profound, by the Earth itself in all its extraordinary complexity, operating on timescales and at scales that routinely exceed our intuition, producing phenomena of genuine strangeness and beauty that reward careful attention and honest investigation with revelations more remarkable than any myth. This is what the frozen world has to teach us if we come to it with the right combination of curiosity, humility, and rigor. Not a comfortable world, not a world that yields its secrets easily or quickly, but a world that is alive in ways both literal and metaphorical, with the deep history of a planet that has been at work for 4.5 billion years, and that is not finished yet, not finished building and breaking and freezing and thawing and preserving and revealing. We have covered much ground in this first part of our journey. We have been to Antarctica and looked beneath its ice shelves at the teeming life that defied our expectations. We have listened to the strange sounds of the Southern Ocean and followed them back to the animals that make them. We have watched the blood-red falls and understood, finally, why iron and time and cold can together create something that looks like the wound of the earth. We have descended into the permafrost and found the wolf pup and the ancient man and the viruses that waited through the ages for the ice to melt. We have visited the frozen mysteries of Alaska, the legendary creatures, the remote research facility, the questions that indigenous traditions have been asking for generations, and we are not finished. In the second part of this journey, we will go further still, into the deep time of the geological record, into the seas where ancient creatures of extraordinary size once swam and have left their bones for us to find. We will go into the ice again, deeper this time, and pull from it records of climates and atmospheres that preceded our species by hundreds of thousands of years. We will follow the explorers and the scientists and the curious and the brave into the last frontiers of the frozen world, and we will find there, as we have found throughout this first part, that the truth, patiently uncovered by careful investigation, is never less remarkable than the mystery that preceded it. The ice remembers, and we are finally learning to read what it has kept for us. We left the first part of this journey standing at the edge of the frozen world, looking out across landscapes of extraordinary complexity and antiquity, landscapes that have been shaped by forces operating over timescales that dwarf anything in human experience, and that preserve within their ice and permafrost and ancient rock a record of the Earth's history so detailed, so complete, and so astonishing that every new investigation seems to yield revelations that redefine what we thought we knew. We visited the underside of Antarctic ice shelves and found thriving ecosystems where we expected emptiness. We listened to the strange acoustic language of the Southern Ocean and traced those sounds back to living animals of surprising variety and behavior. We dug into the permafrost and found a wolf pup who died 57,000 years ago with his whiskers still intact. We stood at the blood falls and understood how iron and time and cold can paint a glacier the color of a wound. Now we go deeper. In this second part of our journey, we will travel further into the frozen past, further into the biological mysteries that the ice has preserved, and further into the questions, scientific and cultural and philosophical, that those mysteries raise. We will encounter creatures of almost impossible size, preserved in rock and in ice. We will follow the ice cores down into climate records that stretch back nearly 1,000,000 years and reveal the rhythms of a planet operating on a scale of time that no human civilization has ever witnessed. We will return to Alaska and dig into its human history with the care and attention it deserves. We will explore what happens when the frozen world begins to change, when the ice that has been a library and a time capsule and a preservation medium begins, for the first time in thousands of years, to yield its secrets not through careful scientific investigation, but through the simple, unstoppable process of melting. And we will end, as every honest investigation of mystery must end, not with all the answers neatly resolved, but with a deeper appreciation of the questions, a sense of the scale and complexity of the world we inhabit, and of the extraordinary privilege it is to be the kind of creature that can ask questions about it. Let us begin again in the deep past, with creatures that no living human eye has ever seen moving through a world that no human being has ever known. Imagine an ocean. Not the ocean we know today with its familiar coastlines and its documented species and its surveyed depths, but an ancient ocean, an ocean of 300 million years ago, or 150 million years ago, or 80 million years ago, when the continents were in different positions, when the climate was different, when the very chemistry of the water was different, and when the creatures that swam through it were of a kind that our world has entirely forgotten. These ancient oceans were not empty. They were not simpler or less complex than the oceans of today. In many ways, they were more biodiverse, filled with organisms that evolution had spent hundreds of millions of years developing, organisms that filled ecological roles that have no modern equivalent, organisms of a size and variety that the modern ocean, despite its extraordinary richness, cannot fully replicate. And some of those organisms were enormous, not merely large. Not merely impressive, enormous in a way that challenges the imagination, creatures that make the largest animals alive today seem modest by comparison, or that are simply so different from anything in the modern world that the effort to comprehend them requires a genuine reorientation of the imagination. The fossil record is, of course, how we know about these creatures. The bones and teeth and shells, and occasionally, the soft tissue impressions of organisms that lived in ancient oceans are preserved in the rock that was once the sediment on those ancient ocean floors, and the slow processes of geological change, the uplift of ocean sediments into mountains, the erosion of rock by wind and water and ice, eventually brings those fossils to the surface where, if conditions are right and someone is paying attention, they can be found and studied. Antarctica, again, is a place of extraordinary paleontological significance. Because the continent has been at or near the South Pole for a very long time, long enough for the sedimentary rocks that record its ancient marine history to have accumulated over many geological periods, it preserves a record of ancient ocean life that is, in terms of its temporal completeness, remarkable. And the fossils that have been found in Antarctic rocks span an enormous range of biological complexity and include some of the most spectacular marine reptiles ever recovered. Among the most dramatic of these is the plesiosaur, a group of large marine reptiles that were not dinosaurs technically, but that lived at the same time as the dinosaurs and were, in terms of their ecological role, the top predators of the ancient seas. Plesiosaurs came in two basic body plans: the long-necked, small-headed form associated with the popular imagination of the Loch Ness Monster, and the short-necked, large-headed form sometimes called the pliosaur. Both were large, both were formidable, both were, by any measure, extraordinary animals. The plesiosaurs that have been recovered from Antarctic rocks are among the largest known members of their group. Specimens found in the sedimentary rocks of Antarctica, rocks that were laid down on the floor of the ancient ocean that covered the region before the continent reached its current polar position, include animals that, based on the size of the recovered bones, would have been enormous. The most spectacular of the Antarctic plesiosaur finds is a specimen whose size, when estimated from the recovered skeletal material, suggests an animal of extraordinary dimensions, a creature that would have been among the largest predatory reptiles ever to swim in an ocean. To stand before the fossil bones of one of these animals, even in a museum, even in the clinical setting of a laboratory, is to experience something close to vertigo. The bones are simply too large. They do not fit easily into the mental scale of the living world. The paddle bones, the modified limbs that plesiosaurs used to propel themselves through the water, are broad and flat and massive, suggesting forelimbs of extraordinary power. The vertebrae, stacked in sequence, give an impression of a spine built to support and move a body of immense weight. And the teeth, where they are preserved, are long and conical and sharp, the teeth of an animal that was not filtering plankton or nibbling on coral, but catching and consuming large, active prey in the open ocean. What did a giant plesiosaur eat? The answer, based on gut content analysis where it has been possible, analysis of tooth wear and bite force, and ecological modeling of ancient food webs, suggests that large plesiosaurs were generalist apex predators, eating large fish, cephalopods, and possibly other marine reptiles. Their long necks and the long-necked forms may have been used to reach into schools of fish or to maneuver their heads into positions that allowed them to snap up prey from angles that would have been difficult for a more rigidly bodied predator to achieve. Their large paddled flippers would have made them powerful and maneuverable swimmers, capable of sustained cruising over long distances as well as rapid bursts of speed when pursuing prey or avoiding larger predators. The world those plesiosaurs swam in was not the world we know. The ocean of the Mesozoic era, the era of the dinosaurs, spanning roughly from 250 million years ago to 66 million years ago, was in many ways more extreme than the modern ocean. Temperatures were generally higher. Sea levels were in many periods substantially higher than today. The ocean chemistry was different, with higher concentrations of dissolved carbon dioxide and different patterns of acidity and salinity in different regions. And the biological communities of that ocean were configured differently, different groups of organisms filling different ecological roles, with different evolutionary relationships and different histories. The end of the Mesozoic, the mass extinction event 66 million years ago, associated with the impact of a large asteroid and possibly with massive volcanic activity, extinguished the plesiosaurs along with the non-avian dinosaurs and a substantial fraction of all the species then living on Earth. The marine ecosystems of the ancient world were restructured, and the new configurations that emerged over the subsequent 66 million years, the Cenozoic era, the era in which we live, are the ones we recognize as the modern ocean. But the bones of the ancient ocean are still in the rock, still waiting. In Antarctica and on other continents, in the sedimentary rock that was once the floor of Mesozoic seas, the record of that lost world persists, fragmentary, incomplete but genuine, yielding to patient investigation, a picture of biological complexity and variety that reminds us how much the Earth has experienced and changed and lost and rebuilt in the vast span of its history. The deep geological record that fossils provide, a record of biological life over hundreds of millions of years, is complemented for more recent history by the record preserved in ice. We discussed ice cores in the first part of this documentary, but the full significance of what ice cores tell us deserves more careful attention because it speaks to something that is both scientifically fundamental and philosophically profound. An ice core is physically a cylinder of ice, typically about 10 centimeters in diameter and varying in length from a meter or less for near-surface samples to many meters for deeper samples, drilled from an ice sheet using specialized drilling equipment. The process of drilling an ice core is painstaking, technically demanding, and logistically challenging in the extreme, particularly when the drilling is taking place in Antarctica or Greenland, where weather conditions can be ferocious and where the remoteness of the site creates supply and transport challenges that require careful planning and significant resources. But the reward for that effort is extraordinary. Each core is a cylinder of time. The top of the core represents the most recent snow accumulation, the last year or two of snowfall. The bottom of the core, if the drilling has gone deep enough, can represent snowfall that occurred hundreds of thousands of years ago, and every layer in between, laid down year by year in a continuous sequence, preserves a record of the atmospheric conditions at the time it was deposited. How do scientists read this record? The primary tool is the analysis of the ice itself, specifically the ratios of different isotopes of oxygen and hydrogen within the water molecules that make up the ice. These ratios vary depending on the temperature at which the water evaporated from the ocean and at which the snow fell from the cloud. Warmer conditions produce different isotopic ratios than colder conditions, and this relationship is consistent enough that the isotopic composition of ancient ice can be used to reconstruct the temperature at the time the snow was deposited, with an accuracy sufficient to distinguish between periods of glacial maximum, ice ages, and interglacial periods of relative warmth like the one we are currently living in. But the ice also contains, trapped within its crystal structure, tiny bubbles of ancient air that was sealed into the ice at the time the snow compacted into glacial ice, bringing with it a sample of the atmosphere as it existed at that moment. These air bubbles preserve, with extraordinary fidelity, the composition of the ancient atmosphere, including the concentration of greenhouse gases like carbon dioxide and methane. Analysis of air bubbles in ice cores has provided the most direct and complete record available of how atmospheric greenhouse gas concentrations have varied over the past 800,000 years. That record is remarkable in its clarity and in what it reveals. It shows that atmospheric carbon dioxide and temperature have been tightly linked over the past 800,000 years, that during ice ages, both carbon dioxide and temperature were lower, and during interglacials, both were higher. It shows that this relationship has been consistent across multiple glacial-interglacial cycles, with a regularity that speaks to the fundamental role of greenhouse gases in regulating Earth's climate on glacial timescales. And it shows with striking clarity the departure of the modern atmosphere from anything in the 800,000-year record, a departure that is, in the scale of the ice core record, essentially instantaneous, occurring over a geological eye blink of a few centuries. The ice core record also contains evidence of other atmospheric events. Volcanic eruptions, for example, are recorded as thin layers of sulfuric acid particles in the ice, allowing scientists to construct a detailed timeline of major volcanic events going back hundreds of thousands of years. The eruption of Tambora in 1815, which caused the so-called year without a summer in the following year, appears as a distinct chemical spike in ice cores. So does the much larger eruption of Toba, a supervolcano in what is now Indonesia, approximately 74,000 years ago, an eruption so enormous that it may have dramatically reduced the human population at the time, and whose signature appears clearly in ice cores from both the Greenland and Antarctic ice sheets. Dust layers in ice cores reveal periods of intense aridity and windiness in the past ice age conditions, when reduced vegetation cover and dry climates sent vast amounts of dust into the atmosphere, and that dust eventually settled onto the growing ice sheets and was preserved there. Sea salt layers tell of periods of enhanced storminess. Traces of pollen and other biological materials carried on the wind from distant continents provide information about vegetation and surface conditions at specific times in the past. The ice core is, in short, one of the most extraordinary scientific archives ever discovered, a multi-proxy record of atmospheric and environmental conditions with a temporal resolution in the best preserved sections of individual years or even seasons, and a total span reaching back nearly 1,000,000 years. It is a record that no other natural archive can fully replicate, and its study has fundamentally transformed our understanding of the dynamics of Earth's climate system. The scientists who extract and analyze ice cores work in conditions that are, by any standard, challenging. The drilling sites in Antarctica, deep in the interior of the continent, at elevations of 3,000 meters or more above sea level, where temperatures in winter fall below -60 degrees Celsius, and the altitude makes the already cold air thin enough to cause altitude sickness, are among the most physically demanding research environments on Earth. The cores must be kept cold throughout their extraction, transport, and analysis, because warming would cause the ice to recrystallize and the trapped air bubbles to migrate, compromising the integrity of the record. The logistics of maintaining cold chain transport from a drilling site in the interior of Antarctica to a laboratory in Europe or elsewhere requires careful planning and significant infrastructure. But the people who do this work, and there are hundreds of them, representing dozens of institutions and many countries, do it with a passion and commitment that speaks to the power of what the ice holds. They are, in the most literal possible sense, reading the past. They are extracting from the ice a record of atmospheric conditions that no human being witnessed, that predate our species, that encompass climate events of a scale and violence that no civilization has ever experienced directly. And they are using that record to understand where the climate has been, and in doing so, to inform our understanding of where it might be going. The frozen world of the deep past, the ancient ocean of the plesiosaurs, the Ice Age climate recorded in cores drilled from glacial ice, connects to the human story in ways that are sometimes unexpected and always profound, because the climate of the Earth has not been static during the period of human existence. On the contrary, the past 100,000 years, the period during which our species evolved to its modern form and spread across the planet, has been a time of dramatic climate variability, with ice ages and warm periods alternating at frequencies determined by the astronomical rhythms of the Earth's orbit and rotation. The maximum of the last ice age, which occurred roughly 20,000 years ago, was a world radically different from the one we inhabit today. Ice sheets covered vast areas of the northern hemisphere, sheets kilometers thick, extending south to roughly the latitude of what are now major population centers in the northern hemisphere. Sea levels were dramatically lower, perhaps 120 meters lower than today, because an enormous fraction of the world's water was locked up in those ice sheets rather than in the ocean. Coastlines were in completely different positions. Lands that are now seabed were then dry, habitable terrain. And some of those lands were of extraordinary importance to the human story. Beringia is the name given to the land bridge that connected what is now northeastern Asia to what is now Alaska during periods of low sea level. At the maximum of the last ice age, Beringia was not a narrow bridge but a vast continental shelf exposed by the low sea level. A broad, tundra-covered landscape hundreds of kilometers wide, populated by mammoths, bison, horses, and a diverse fauna of Ice Age herbivores and the predators that followed them. And through this landscape, at some point, the timing is still debated, with estimates ranging from roughly 20,000 to 30,000 years ago or even earlier, human beings walked. They walked from Asia into what would become the Americas. This is one of the most consequential migrations in the history of our species. The peopling of the Americas, the spread of human populations through two continents that, until that moment, had never known the presence of our kind, set in motion 14,000 years or more of independent cultural, technological, and biological development. The peoples who eventually populated the entirety of North and South America, from the Arctic to the tip of Tierra del Fuego, are the descendants of those first Beringian migrants. Their diversity in language, culture, technology, spiritual practice, social organization reflects the extraordinary adaptability of the human species and the creative diversity that emerges when human populations have time, space, and isolation in which to develop their own solutions to the challenges of existence. Alaska is where that story begins, in the Americas. The earliest archaeological sites in Alaska, sites that document the presence of human beings in the state, date to approximately 14,000 years ago, though some researchers argue for earlier dates based on genetic evidence and on the characteristics of the earliest tool traditions. These earliest Alaskans were not simple or primitive people. They were fully modern human beings, cognitively and biologically identical to us, equipped with sophisticated tool kits, complex social organization, deep knowledge of their environment, and the full range of human intellectual and creative capacities. They were simply living in a very challenging environment, and they were meeting that challenge with intelligence and adaptability. The trace they left in the Alaskan archaeological record is, by the standards of much younger sites, sparse. Permafrost conditions, while extraordinary for the preservation of biological material, are in some ways less favorable for the preservation of the kinds of evidence, hearths, middens, structures, that archaeologists typically use to reconstruct ancient human behavior. And the sheer remoteness and difficulty of access of many potential archaeological sites in Alaska means that systematic survey has been, in many areas, limited. But the evidence that has been found is genuinely remarkable. Stone tools from Alaska's earliest archaeological horizons reflect technological traditions that connect to the broader world of Siberian and Central Asian prehistory, traditions brought by the first migrants across Beringia and adapted to the specific resources and challenges of the Alaskan environment. Animal bones from these sites, bearing the marks of human cutting and processing, document the exploitation of the full range of megafauna then present in Alaska: mammoths, bison, horses, and other large herbivores that would, over the subsequent millennia, disappear from the Alaskan landscape, leaving behind only their frozen remains in the permafrost. The relationship between the first Alaskans and the extinction of the Pleistocene megafauna is one of the most debated questions in all of North American prehistory. Did human hunters drive these species to extinction, or were they already in decline due to climate change, and did human hunting simply deliver the final blow to populations already stressed by the environmental upheavals of the end of the Ice Age? Or is the explanation something more complex, a combination of factors, varying in their relative importance from species to species and region to region, that together produced the remarkable biological impoverishment of the Americas that occurred at the end of the Pleistocene? The evidence is genuinely ambiguous, and honest scientists acknowledge that ambiguity. What is clear is that the timing of the megafaunal extinctions in the Americas corresponds closely to both the arrival of human populations and the rapid climate changes of the late Pleistocene, and that disentangling the relative contributions of these factors across an entire continent in a period of several thousand years is extraordinarily difficult. The frozen remains of the megafauna, the mammoths and the horses and the bison preserved in Alaskan and Yukon permafrost, are among the most important data sources available for addressing these questions, because they provide biological samples that can be dated precisely and analyzed genetically to reveal information about population sizes and trends in the millennia before extinction. Let us now go somewhere specific within Alaska, somewhere that represents in concentrated form the intersection of ancient human presence and extraordinary natural preservation that makes this region such a remarkable place for understanding the deep human past. Let us go to the coast. The coastlines of Alaska are among the most biologically productive environments on Earth. The cold, nutrient-rich waters of the Gulf of Alaska and the Bering Sea support extraordinary abundances of fish, marine mammals, and seabirds, and they have supported human populations for thousands of years. The maritime peoples of the Alaskan coast, the Aleut or Unangan people of the Aleutian Islands, the Alutiiq people of the Kodiak Island area and the Alaska Peninsula, and the Yupik and Inupiat peoples of the western and northern coasts developed cultures of extraordinary sophistication, centered on the exploitation of marine resources with tools and techniques that represented the culmination of thousands of years of accumulated knowledge and innovation. The Unangan people of the Aleutian Islands are particularly remarkable in this context. They inhabited one of the most extreme maritime environments on Earth, a chain of volcanic islands stretching for nearly 2,000 kilometers across the North Pacific, battered by some of the most severe weather in the world, surrounded by ocean of extraordinary depth and ferocity. And they did so with a culture so precisely tuned to that environment that they could move through it with a facility that astonished the European explorers who first encountered them. The Unangan developed, among their many technological innovations, the Bioduck, a form of kayak so superbly designed for the conditions of the North Pacific that modern kayak designers, examining historical examples, have been impressed by the sophistication of its hydrodynamic principles. The Bioduck was not merely a boat. It was a precision instrument, developed through generations of iterative refinement, so closely matched to the specific conditions of Aleutian waters that its makers could travel safely through ocean conditions that would have been simply lethal in any other watercraft available to them. The archaeological sites of the Aleutian Islands have provided a remarkable record of Unangan culture going back thousands of years, and in some cases, the preservation conditions, while not as spectacular as permafrost, have been good enough to preserve organic materials of great scientific interest. Middens, the refused deposits of ancient settlements containing the bones of the animals that were eaten, the tools that were used and discarded, and occasional human burials have been excavated at sites throughout the islands, building up a detailed picture of Anangan life over deep time. Among the most remarkable discoveries from Aleutian archaeological sites are the Aleut mummies, human burials in which the bodies were prepared in a specific way before interment in dry caves or rock shelters, and in which the combination of the drying technique and the naturally cool, dry conditions of the caves has produced a degree of preservation that, while not equal to permafrost mummies, is nevertheless extraordinary. The Aleut mummies provide direct biological evidence of the health, diet, and genetic affinities of the historical Anangan population, evidence that, combined with the archaeological record of their material culture, paints a remarkably complete picture of a human community adapted to one of the world's most challenging environments. The study of these mummies has required careful collaboration between scientists and the descendant communities whose ancestors they represent. This collaboration, sometimes challenging, always necessary, reflects a broader shift in the relationship between archaeology and indigenous communities that has been underway for several decades. The recognition that the objects and remains recovered from archaeological sites are not merely scientific specimens, but are connected to living communities with their own relationships to their past has fundamentally changed how archaeological research is conducted, and in most cases has resulted in better science as well as more ethical practice. The Anangan people are still here. They still inhabit the Aleutian Islands. They still carry in their language and their culture and their knowledge of the sea and the islands the accumulated wisdom of thousands of years of life in one of the world's most demanding environments. The archaeological record of their past and the mummies that represent their ancestors are part of a living heritage, not merely historical curiosity. The question of ancient mummies in the frozen and near-frozen environments of the North connects to a much broader phenomenon of remarkable preservation that has been documented in multiple locations and across multiple time periods. We have discussed Ötzi the Iceman, the Neolithic man preserved in the Alps. We have discussed the permafrost mummies of large animals in Alaska and the Yukon. Let us now consider what it means more generally for preservation of this quality to be possible, what it reveals about the frozen world and about the fragility and resilience of biological material. Preservation of the kind that produces a mummified body with soft tissue intact requires, essentially, a race between preservation and decomposition. The normal fate of a dead organism is decomposition, the breakdown of biological structures by bacteria, fungi, and the chemical processes of oxidation, hydrolysis, and other reactions that, in the presence of moisture and appropriate temperatures, proceed rapidly. A body left at room temperature in a humid environment will be reduced to bones within weeks or months. The speed of this process is astonishing. The complex biological architecture of a body built over a lifetime can be erased in a season. What freezing does is stop this process. At temperatures below freezing, bacterial metabolism slows dramatically and eventually ceases. The chemical reactions of decomposition, which depend on liquid water as a medium, cannot proceed when the water is ice. And in the specific conditions of deep permafrost, where temperatures remain below freezing year-round, where the frozen ground excludes air and its oxygen, and where the body is sealed from the surface world by overlying layers of sediment, the result can be preservation of extraordinary completeness and duration. But freezing alone is not sufficient. The transition from death to frozen preservation must be rapid enough to prevent significant decomposition. An animal that dies in summer and lies exposed on the tundra will decompose substantially before winter cold freezes it, and the resulting preservation will be poor. An animal that dies in winter, or that falls into a frozen lake or a snow-filled crevasse, or that is buried by a sudden landslide or volcanic eruption under conditions where freezing occurs quickly. These are the circumstances that produce the spectacular specimens that emerge from Alaskan and Siberian permafrost. The wolf pup almost certainly died in winter, or was buried very quickly under conditions that brought his body into contact with frozen ground before decomposition could begin. The mammoths and horses and bison that have been recovered from permafrost similarly died or were entombed in ways that initiated rapid freezing. These were accidents of circumstance, the right place at the right time, or rather the wrong place at the right time, that resulted, through a sequence of events spanning tens of thousands of years, in the emergence of biological time capsules of a kind that no deliberate preservation technique could replicate. The implications of this understanding are significant for what we expect to find in permafrost as more of it is excavated, by mining operations, by construction projects, and by the processes of thaw that are increasingly exposing ancient layers of frozen ground. More specimens await discovery. More wolf pups, more horses, more mammoths, and perhaps, at some sites, more human remains of an age and completeness that would transform our understanding of the ancient inhabitants of the North. The permafrost is a vault whose contents are only beginning to be inventoried, and each new discovery from it is a reminder of how much remains locked in the frozen ground, waiting for the circumstances that will bring it to light. The processes of thaw that are now exposing ancient permafrost contents are, of course, driven by changes in climate that are occurring at a pace and scale without precedent in the ice core record of the past 800,000 years. The warming of the high latitudes, a warming that has been particularly rapid in recent decades, proceeding at a rate roughly 2 to 3 times faster than the global average, is having profound effects on every aspect of the Arctic and subarctic environment. And while this documentary is not about the political or policy dimensions of climate change, the scientific reality of what is happening to the frozen world is inseparable from any honest account of that world. The permafrost is thawing. This is documented across Alaska, Canada, Russia, and other high-latitude regions. The depth of the seasonally thawed layer, the active layer that freezes in winter and thaws in summer, is increasing. Permafrost that has been frozen for thousands of years is beginning to thaw in its upper portions. The ground surface in areas underlain by permafrost is subsiding as the ice within the permafrost melts and the structural support it provides is lost, a process called thermokarst, which produces a characteristic landscape of irregular depressions, ponds, and tilted or sunken structures that can make formerly stable ground look as if it has been stirred by some vast underground force. The consequences of permafrost thaw for human infrastructure are significant and are already being experienced by communities across the Arctic and subarctic. Buildings, roads, pipelines, and other infrastructure that were built on the assumption of stable, permanently frozen ground are being undermined by the subsidence of thawing permafrost. Communities that have existed for generations in particular locations are finding that the ground beneath them is no longer stable and in some cases are facing the prospect of relocation. But the consequences of permafrost thaw extend beyond infrastructure and beyond human communities into the fundamental functioning of Arctic ecosystems. The vegetation that covers permafrost landscapes, the tundra, with its mosses and sedges and low shrubs and wildflowers, is adapted to the specific conditions created by the presence of permafrost beneath the soil. When permafrost thaws, the soil drainage patterns change, the soil moisture changes, and the vegetation communities shift in response. Areas that were once dry tundra can become waterlogged as thawing permafrost creates ponds and wetlands. Areas that were once wetland can dry out as drainage patterns shift. The result is a landscape in transition, a mosaic of changing conditions, each patch evolving at its own pace, creating a complexity of ecological change that is difficult to monitor and even more difficult to predict. For wildlife, the changing landscape of the Arctic presents challenges of extraordinary complexity. Species that have evolved over thousands of years to exploit specific resources in specific environments are finding those environments in flux. The ice that seals the ocean in winter, the sea ice that provides hunting platforms for polar bears and resting places for walrus and seals, is declining in extent and duration. The timing of seasonal events, the flowering of tundra plants, the emergence of insects, the hatching of migratory birds' eggs is shifting, and the complex synchronized relationships between species that depend on that timing are being disrupted. The stability of the frozen world, the very quality that makes it such an extraordinary archive of the past, is being compromised. But the thawing permafrost is also, paradoxically, revealing the very evidence that helps us understand what is being lost. The ancient specimens that emerge from thawing permafrost, the frozen animals, the ancient plant material, the preserved microorganisms, are products of the permafrost preservation system and are only accessible because that system is being disrupted. There's a bitter irony in the fact that the conditions producing some of the most remarkable natural history discoveries of our time are the same conditions that are threatening the ecosystems those discoveries come from. Let us return one final time to Antarctica to complete our picture of the frozen South before moving toward the conclusion of this documentary. Because there is one aspect of Antarctic science that we have not yet fully explored, one dimension of the continent's extraordinary character that speaks most directly to its role as a frontier of human knowledge and a place where the boundaries of the possible continue to be redrawn. The deep ice of Antarctica, the ice that has been accumulating for millions of years, layer upon layer in the cold heart of the continent, is not perfectly uniform. Beneath the ice, the landscape of the continent, the mountains and valleys and plains of bedrock that the ice sheet covers, is extraordinarily complex. And that complexity influences the ice above it in ways that are scientifically significant and sometimes unexpected. In the mountains of East Antarctica, the Transantarctic Mountains, which extend for more than 3,000 kilometers across the continent, separating the East and West Antarctic ice sheets, there are places where the ice sheet is thin enough, and where the combination of geological factors is specific enough, that ancient ice that may be more than 1,000,000 years old, is preserved in accessible locations. These places, known to glaciologists as blue ice areas, are sites where the ice flows upward against an obstacle and is stripped away at the surface by the powerful katabatic winds that flow down from the high polar plateau, exposing the ancient ice beneath. In some blue ice areas, the ice at the surface may be hundreds of thousands of years old enough to record climate conditions that predate the current limit of the ice core record. Scientists are actively searching for blue ice areas in Antarctica where ice more than 1,000,000 years old may be accessible at or near the surface. Ice that could, if found and successfully sampled, extend the ice core record back to a time when the cycle of glacial and interglacial periods operated differently than it does today. There is a particular scientific interest in the transition that occurred roughly 800,000 years ago, when the dominant cycle of glaciation shifted from a roughly 40,000-year cycle to the roughly 100,000-year cycle that has characterized the past 800,000 years. Understanding what drove this transition, why the Earth's climate system shifted from one dominant rhythm to another, requires data from before the transition, data that is not yet available from existing ice cores. The search for accessible ancient ice in Antarctic blue ice areas is one of the major scientific endeavors currently underway on the continent. The technology required to find, access, and analyze ice of this age is at the absolute frontier of what is currently possible. Radar systems mounted on aircraft or on ground-based vehicles can peer through the ice and map the internal layering, identifying areas where ancient layers are preserved near the surface. Ground-penetrating radar can reveal the structure of the ice in the immediate vicinity of potential drilling or sampling sites. And the drilling itself, extracting a core from ice that may be 1,000,000 years old without contaminating or damaging the fragile climate record within it, requires equipment and techniques of extraordinary precision. This is science at its most demanding and most rewarding. The effort required, the logistics, the engineering, the technical skill, the physical endurance required of the scientists and technicians working in conditions of extreme cold and remoteness is enormous. And the reward, a cylinder of ancient ice, brought back from the frozen interior of a continent at the bottom of the world, containing bubbles of air that were sealed into the ice before the first member of our species drew breath, is, in the most literal sense, irreplaceable. No other source of this data exists. No other way of accessing this record of the ancient atmosphere is available to us. The ice is unique, and what it contains is unique, and the effort to extract and preserve and analyze it is entirely justified by its extraordinary scientific value. Beyond the drilling and the robots and the ice cores and the frozen specimens, there is another dimension of the Antarctic story that deserves attention, the human story of those who have gone to this place, who have lived there and worked there and in some cases died there, and who have returned with knowledge that has changed the way we understand our world. The history of human presence in Antarctica is short by the standards of the other continents. The first confirmed sighting of the Antarctic continent occurred in 1820, and the first verified landing on the continent itself took place in 1895. The heroic age of Antarctic exploration, which lasted from the late 19th century to the early 20th, sent expeditions of extraordinary ambition and remarkable suffering into the interior of the continent, pursuing the geographic poles and the scientific understanding that went with them. The names of that era, Shackleton, Scott, Amundsen, Mawson, are associated with feats of endurance and navigation that remain astonishing even by the standards of modern adventure. Ernest Shackleton's expedition of 1914 to 1916 is perhaps the most extraordinary survival story in the history of polar exploration. A story of a ship crushed by sea ice, a crew stranded on the drifting ice pack, an open boat voyage of 800 miles through the most dangerous seas on Earth, and a crossing of the mountains and glaciers of South Georgia Island to reach a whaling station and organize a rescue. A rescue that succeeded in bringing every single member of the expedition home alive. The story of Shackleton's endurance expedition is a masterclass in leadership, perseverance, and the will to survive, and it has been told and retold because it speaks to something fundamental about the human capacity to face extremity with grace and determination. Robert Falcon Scott's expedition to the South Pole in 1911 and 1912 ended in tragedy. Scott and his 4 companions reached the pole only to find that Amundsen had preceded them by 34 days, and all 5 died on the return journey, overtaken by brutal weather and exhausted beyond the point of recovery. The diaries that Scott kept until the final days of his life, found with the bodies months later by a search party, are documents of remarkable dignity and courage, a record of suffering faced with clarity and without self-pity. These early explorers were not just adventurers, they were scientists. They carried with them meteorological instruments, geological sampling equipment, biological collection apparatus, and the observational skills required to use them effectively. The scientific data they collected, geological samples, weather records, biological specimens, formed the foundation of Antarctic science, establishing the baseline observations against which a century of subsequent research has been measured. And in their courage and their curiosity, they embodied the spirit that continues to drive Antarctic research today, the conviction that understanding this extraordinary place is worth the extraordinary effort required. Today, Antarctica is governed by the Antarctic Treaty System, a remarkable international agreement signed in 1959 and now adhering to nearly 60 nations, under which the continent is set aside for peaceful scientific research and protected from national territorial claims and military activity. The research stations that now dot the continent, at least 70 permanent stations operated by dozens of countries, housing populations that range from a handful of people in winter to several thousand in summer, represent a sustained international commitment to understanding a place that has no permanent human inhabitants, but that is, as we have seen throughout this documentary, of extraordinary importance to our understanding of the Earth. The scientists who work in those stations, the geologists and glaciologists and biologists and atmospheric scientists and oceanographers and astronomers who spend months or years of their careers at the bottom of the world, are continuing the tradition of those early explorers, but with tools and methods and safety systems that make their work, while still challenging, more productive and less immediately life-threatening. They return with data and specimens and insights that fill the journals of their fields, and occasionally reach a broader audience as examples of the extraordinary things that happen when human curiosity and technological capability combine to address the mysteries of the natural world. Now let us bring these threads together: the ancient ocean, the frozen specimens, the acoustic mysteries, the subglacial lakes, the deep ice cores, the indigenous knowledge systems of the North, the legendary creatures of Alaskan tradition, the radio facility in the wilderness, the thawing permafrost, and ask what they collectively reveal about the frozen world and our relationship to it. The frozen world, Antarctica and the Arctic, the permafrost regions and the mountain glaciers, the sea ice and the ice shelves, is not a marginal or peripheral part of the Earth system. It is central to it. The ice sheets of Antarctica and Greenland together contain enough fresh water to raise global sea levels by more than 70 meters if they were to melt completely. The sea ice that forms each winter in the Arctic and Antarctic modulates the heat exchange between ocean and atmosphere across enormous areas of the planet, affecting weather patterns and ocean circulation on hemispheric scales. The permafrost of the high latitude stores vast quantities of carbon that, if released, would significantly alter the composition of the atmosphere. The frozen world is also central to the human story in ways that are not always recognized. The ice ages that shaped the frozen world also shaped our species. The human populations that spread across the globe during the Pleistocene were shaped by the glacial and interglacial cycles, channeled by ice sheets into specific migration routes, forced to adapt to changing environments, and ultimately distributed across the planet in the pattern we see today as a result, in part, of the waxing and waning of the great ice sheets. Beringia, the land bridge created by the low sea levels of the last ice age, made possible the peopling of the Americas. The end of the last ice age, the warming that melted the ice sheets and raised sea levels and transformed the climate of every region on Earth, set the stage for the development of agriculture and the rise of the first civilizations. We are ice age children. Our species evolved during the Pleistocene in a world of cycling ice ages and interglacials, and every human population on Earth carries in its genome and its culture the marks of that icy history. The frozen world is not alien to us. It is, in the deepest sense, part of our origin story. And the mysteries that the frozen world contains, the mysteries we have been exploring throughout this documentary, are not merely exotic curiosities, interesting but irrelevant to the human condition. They are windows into the history of life and of the planet that produced us. The ancient viruses preserved in permafrost speak to the resilience of biological information across time. The ecosystems beneath Antarctic ice shelves speak to the adaptability of life in extreme conditions. The ice core record speaks to the relationship between atmospheric chemistry and climate that has governed the habitability of Earth for hundreds of thousands of years. The frozen specimens of Pleistocene megafauna speak to the dynamics of extinction and ecological change that are directly relevant to the conservation challenges of our own time. Each mystery, when investigated with care and honesty, yields knowledge that connects to a broader web of understanding. Each strange sound in the Southern Ocean, when traced to its source, reveals something about the biology of whales and the functioning of marine ecosystems. Each anomalous formation on a satellite image of Antarctica, when examined in the field, reveals something about the geological processes that shape frozen landscapes. Each frozen body pulled from the permafrost, when analyzed with the tools of modern biology, reveals something about the populations and ecosystems of the past. This is the deeper lesson of the frozen world. That mystery, engaged with honestly and rigorously, is not the opposite of knowledge but its beginning. Every question answered opens the door to deeper questions. Every discovery reveals the contours of a larger unknown. And the frozen world, patient, ancient, cold, and extraordinarily well preserved, has a practically inexhaustible supply of both. There's a quality to the frozen places of the earth that is difficult to describe, but that virtually everyone who has spent time in them reports in some form. It is a quality of presence, of being in a place that is, in some fundamental way, more real than more familiar environments, more immediate, more absolute. The cold is not a metaphor in Antarctica or in the high Arctic. It is a physical reality that demands constant attention, that limits everything you do and shapes every decision you make. The scale of the landscape, the vast, featureless white expanse of the Antarctic plateau, or the equally vast, rolling tundra of the Alaskan interior, produces in most people a kind of profound humility that is, paradoxically, not diminishing but expanding. You feel small in these places. You feel your smallness with a clarity that is almost physical. And that feeling of smallness is accompanied, for many people, by a corresponding sense of the immensity and significance of the world around them. Scientists who work in these environments frequently describe this quality, this sense of being in the presence of something much larger than themselves, much older than themselves, much more powerful than themselves. The ice is 4 kilometers thick beneath their feet. The oldest ice in it has been there for 1,000,000 years. The continent beneath the ice was once tropical forest. The ocean around it teems with life that has never seen sunlight. The sounds that drift through its waters have been drifting there, in some cases, since before the first human city was built. The scale of it, temporal, spatial, biological, exceeds the normal operating parameters of human intuition, and in that excess, in that gap between what the mind can easily grasp and what is actually present, something happens that is hard to articulate but that is clearly important. It may be that this quality, this capacity to induce a productive sense of scale and humility, is one of the most important things the frozen world has to offer. Not just its scientific data, as extraordinary as that is, not just its preserved specimens and its climate records and its undiscovered ecosystems, but the experience of it, the direct, physical encounter with an environment that operates on timescales and at scales that dwarf the human, has a value that is not reducible to scientific or practical terms. The indigenous peoples who have lived at the edges of the frozen world for thousands of years understand this in ways that scientific institutions are only beginning to appreciate. Their traditions of respect for the land and the sea and the ice, their protocols for engagement with the non-human world, their ways of naming and categorizing, and understanding the complex phenomena of their environments, these are not primitive or naive responses to a world they did not understand. They are sophisticated adaptations, evolved over thousands of years, for living in relationship with an environment of extraordinary power and complexity. They reflect a depth of engagement with the frozen world that no visiting scientist, however brilliant and well-equipped, can fully replicate in a season or two of field work. The legends of the hairy man and the cute and the kupal, which we mentioned in the first part of this documentary, are part of this broader framework of indigenous engagement with the northern wilderness. They encode knowledge about how to behave in the wilderness, about the dangers and wonders that the landscape contains, about the appropriate relationships between human beings and the non-human world, in a form that is both accessible to community members of all ages and capable of carrying complex information across many generations. They are, in their own way, a kind of knowledge system as sophisticated as the scientific knowledge systems that have been developed in academic and research institutions, but operating according to different principles and serving different functions. The encounter between these two knowledge systems, indigenous and scientific, is one of the most intellectually productive encounters of the present age, when it is conducted in good faith and with mutual respect. Indigenous peoples who know the behavior of sea ice intimately, from years of traveling and hunting on it, have contributed to scientific understanding of how ice forms and changes in ways that instrument-based observation alone could not achieve. Scientists who bring knowledge of the geological and biological processes underlying the phenomena that indigenous traditions describe have helped indigenous communities interpret changes in their environments in ways that both validate traditional observations and place them in a broader context. The synthesis is richer than either tradition alone, and it is a model for how knowledge systems that operate according to different principles can complement and strengthen each other. We have journeyed far in this documentary. We have been to the bottom of the world and to the edges of the top of it. We have gone into the dark water beneath Antarctic ice shelves and watched the cameras of robotic explorers reveal communities of organisms that should not, by previous scientific understanding, be there. We have listened to the Bloop and the Bioduck and the Biotwang and traced each mysterious sound back to its living source. We have stood at the blood falls and understood the chemistry of iron and time. We have knelt beside the frozen body of a wolf pup who died before the pyramids of Egypt were built and marveled at the completeness of the frozen world's memory. We have drilled into the ice and read the atmospheric record of 800,000 years. We have walked the shores of ancient oceans and tried to imagine the creatures that moved through them, plesiosaurs of extraordinary size, ancient whales, creatures that have no living equivalent. We have visited the peculiar and extraordinary HAARP facility in the Alaskan wilderness and tried to understand both what it actually does and why it has become such a focus of speculation and legend. We have engaged with the indigenous traditions of the North, the creatures of legend, the knowledge of ice and sea and tundra accumulated over thousands of years, and tried to approach them with the respect and seriousness they deserve. We have considered what it means that the permafrost is thawing, what is being lost and what is being revealed, and how those two processes are, in a fundamental way, the same process operating on different timescales. What have we learned? What is the takeaway from all of this, from the journey through the frozen world and its extraordinary mysteries? Perhaps the most important thing is this: the frozen world is not what most people picture when they think of it. It is not a void. It is not a blank, featureless, lifeless expanse. It is a world of extraordinary complexity and activity, of thriving ecosystems in unexpected places, of biological communities operating according to principles that challenge our assumptions about where life can exist, of climate records of astonishing detail and duration, of preserved specimens that bring the distant past into vivid, tangible presence. It is a world with a human history that, while shorter than the histories of other regions, is remarkable for the sophistication and resilience of the cultures that developed within it. And it is a world that is, for all its apparent stasis and permanence, in a state of change that is proceeding at a pace that the ice core record reveals to be without precedent in the relevant climate history of the planet. The mysteries that remain, and there are many, are not the mysteries of the sensationalized headline or the viral image. They are not the mysteries of ancient civilizations building pyramids in Antarctica or secret installations controlling the weather from the Alaskan wilderness. They are more interesting than that. They are the mysteries of an ecosystem beneath miles of ice whose energy sources and species diversity are not yet fully understood. They are the mysteries of the viruses preserved in permafrost and what their revival means for our understanding of biological information and its persistence through time. They are the mysteries of the ancient ice, older than 1 million years, that may still be accessible in blue ice areas of the Antarctic interior, and that contains climate data we have not yet been able to read. They are the mysteries of the languages and traditions of indigenous peoples that encode observations and knowledge about the frozen world accumulated over thousands of years, and not yet fully integrated into the scientific framework that is trying to understand the same phenomena from a different angle. These are real mysteries. They are worth pursuing. They are worth the cold and the darkness and the cost and the effort and the time. And they will yield to the patient and careful investigator revelations that are consistently more remarkable than the myths they replace. The doorway that the title of our documentary mentions, that 220-year-old opening in Alaskan rock, is, in the end, a metaphor as much as it is a physical feature. Every investigation of the frozen world begins with something that looks, at first glance, like a doorway, an opening in the apparent surface of things, an anomaly that invites closer inspection, a detail that does not immediately fit the established picture and therefore demands attention. The doorway of the scientist is a mystery, a data anomaly, an observation that challenges the current model. The doorway of the explorer is a gap in the map, a region not yet surveyed, an environment not yet described. The doorway of the storyteller is a legend, a tradition, an account that has been passed down through generations and whose origins and meanings are not immediately obvious to the outside observer. All of these doorways, when you walk through them, when you commit to the investigation, the exploration, the respectful and attentive listening that is required to understand what is on the other side, lead to the same place. They lead to a deeper understanding of the world, not a complete understanding, not a final understanding. Understanding is not a destination you reach, but a process you undertake, and it is a process without end, because the world is larger and older and more complex than any framework we build to describe it. The frozen world teaches this lesson with particular clarity, because it operates on timescales that make our frameworks feel small, and because it preserves evidence of its own history with a completeness that makes the gap between what we know and what there is to know visible in ways that more rapidly changing environments cannot provide. When you hold a piece of ice that has been frozen for 1,000,000 years, or look at the image of a wolf pup who died 57,000 years ago with his whiskers intact, or listen to a recording of a sound that traveled 5,000 kilometers through the ocean and that no one had heard before, you feel the scale of the unknown with physical immediacy. And that feeling, that productive, energizing, humbling feeling of encountering a world larger than your framework for it, is perhaps the greatest gift the frozen world has to offer. Not just the scientific data, not just the preserved specimens, not just the extraordinary ecosystems and the ancient viruses and the climate records of deep time, but the feeling of genuine mystery, of standing at the edge of the known and looking out into the vast, cold, extraordinary unknown beyond. There are more doorways out there. Some of them are literal openings in rock or ice or permafrost that have not yet been explored. Some of them are metaphorical questions that have not yet been asked, connections that have not yet been made, data that has not yet been collected or interpreted. And some of them are in the traditions of people who have been living at the edges of the frozen world for thousands of years, who have been watching and learning and recording in their own way, in their own language, according to their own frameworks, what the ice and the ocean and the tundra and the long polar night have to teach. Walk through them, all of them, with curiosity, with humility, with rigor, and with the willingness to be surprised, because the frozen world is full of surprises. It always has been. And with the extraordinary tools and the accumulating knowledge of the present age, we are, for the first time in the long history of human curiosity about these places, genuinely equipped to begin to understand what the ice has been keeping for us. The ice remembers, and we are learning at last to listen. The story of the frozen world is a story without an ending. Every expedition returns with new questions. Every core drilled from the ice opens a new chapter in a record that extends further back than we have yet been able to read. Every robotic vehicle sent into the dark water beneath the ice shelves comes back with images of creatures and communities that rewrite the ecological maps we thought we had completed. Every thawing permafrost deposit releases another frozen time capsule from the deep past, another specimen that makes the ancient world more real and more particular and more astonishing than it was before. And every legend, every tradition, every indigenous account of a creature or a phenomenon that does not fit neatly into the existing scientific taxonomy. Every one of these, when approached with the combination of respect and rigor that it deserves, reveals something about the complexity of the world and the multiplicity of the ways that human beings have tried to understand and engage with it. The hairy man of Alaskan tradition and the plesiosaur bones recovered from Antarctic rock are not so different in their essential function. Both are accounts, one in the living tradition of an oral culture, one in the preserved record of ancient sediment of creatures that were real, that occupied specific ecological roles, that moved through specific landscapes, and that left traces in the world that human beings in their different ways have been trying to interpret ever since. We interpret the world through the tools we have. Scientists interpret it through instruments and models and experiments and peer review. Indigenous peoples interpret it through accumulated observation, tradition, ceremony, and the specific knowledge systems that their cultures have developed over thousands of years of intimate relationship with specific environments. Both interpretations are partial, both are evolving. And both are pointed at the same ultimate target, the truth of what the world is and how it works. The frozen world is large enough to accommodate both. It is ancient enough to have witnessed the rise and fall of entire ecosystems, of entire genera and families of organisms, of ice sheets that covered continents and then retreated to reveal the landscapes beneath. It is complex enough to continue generating genuine surprises for the most sophisticated scientific programs our civilization can mount. And it is strange enough, cold enough, dark enough, extreme enough to inspire the kind of awe that has always been the beginning of the human impulse to understand. So we end here at the edge of the ice, looking out. The ice extends to the horizon and beyond. Beneath it, in the dark, cold water, something is moving, a giant phantom jelly, perhaps, trailing its 10-meter arms through water that has not seen sunlight since before recorded history. In the permafrost beneath our feet, something is preserved, a creature that walked or flew or swam through a world that no living human has ever known, frozen at a moment in time by a process that was, in the end, an act of extraordinary preservation, a gift from the past to an unimaginable future. In the ice itself, in the layers laid down year by year over hundreds of thousands of years, the record of a climate system operating in its full natural complexity waits to be read by instruments we are still developing and interpreted by minds we have not yet trained. The mysteries are real, the questions are genuine. And the frozen world, patient, cold, ancient, extraordinary, is waiting for us to come back with better tools and deeper curiosity and more honest minds and ask them again. Thank you for watching. Please remember to leave a comment letting us know where you are watching from and what time it is where you are. Your support means everything to this channel, and if you found this journey through the frozen world worthwhile, please subscribe so you never miss the next exploration into the deep mysteries of our extraordinary planet. The ice has more secrets. We will be back for them. Beneath the ice, beyond the cold, and deeper than any human eye has ever seen without the aid of machine and light and courage, there are secrets, ancient secrets, secrets that have been frozen in place for hundreds, thousands, even millions of years, waiting with extraordinary patience for the moment when someone curious enough, brave enough, and equipped enough would finally come looking. That moment has arrived, and what has been found will change everything you thought you knew about the frozen edges of our world. We live on a planet that is still, in so many ways, deeply unknown to us. We have mapped the surface of the moon with greater precision than we have mapped the floors of our own oceans. We have sent probes to the outer reaches of the solar system, past planets so distant they appear as nothing more than faint smudges of light, and yet vast stretches of our own polar regions remain unexplored, unmapped, and utterly mysterious. The ice that covers the poles is not simply frozen water. It is a library. It is a time capsule. It is a living, breathing, shifting archive of everything this planet has ever experienced, every volcanic eruption, every ancient climate shift, every organism that ever drifted through an ancient sea or walked across a frozen plain. And when we begin to look carefully at that archive, what we find is nothing short of extraordinary. This is a documentary about ice, but it is not just about ice. It is about the creatures that live beneath it and within it. It is about the sounds that drift through frozen waters and have baffled scientists for decades. It is about the mountains that look like pyramids and the falls that run with what appears to be blood. It is about ancient men found perfectly preserved in glaciers, wolf pups frozen so completely that their fur and whiskers remain intact after 57,000 years, and viruses so old they were ancient before the first human civilization rose from the banks of a river. It is about doorways that may or may not exist in ancient rock faces in Alaska, about creatures described by indigenous peoples for generations, about facilities built in remote frozen wilderness that have inspired more theories and speculation than almost any other installation on Earth. And it is about the robots, extraordinary purpose-built machines of science, that have been sent into the dark, icy depths where no human could survive, and have returned with images and data that have left the scientific community breathless. We will travel in the course of this documentary to the most remote and extreme environments our planet has to offer. We will go to the bottom of the world and to the top of it. We will go beneath ice shelves that are larger than entire nations. We will go into waters so cold that a human being would lose consciousness within minutes of exposure. We will go into the past, deep, deep into the past, through the evidence locked within layers of ancient ice and the bodies of creatures that have no business being as well preserved as they are. And we will come back with answers. Not all the answers, no honest documentary about science and mystery can promise that, but enough answers to satisfy, and enough remaining questions to keep the wonder alive. Because that is the thing about these frozen places. The more you learn about them, the more mysterious they become. Every answer reveals 3 new questions. Every discovery points toward a deeper layer of the unknown. The ice gives up its secrets reluctantly, one frozen layer at a time, and each revelation arrives with a sense of profound humility, a reminder that the Earth is vast and ancient and complex in ways that dwarf our imagination. So let us begin. Let us go to the ice. Let us start with what has captured the imagination of millions of people around the world. The viral images, the breathless headlines, the social media posts that spread faster than any scientific paper ever could, the claims that something extraordinary, something perhaps inexplicable or even ancient and artificial, has been found in the ice. Doorways, pyramids, sunken ships. Structures that look like they were built by human hands in places where no human civilization has any business having existed. If you have spent any time on the internet in the past decade, you have almost certainly encountered these claims. A photograph of Antarctica taken from above, showing what appears unmistakably to be a pyramid, a perfect 4-sided geometric form rising from the snow, as precise and deliberate in its angles as anything you might find in Egypt. The image circulates. The comments multiply. Was this built by an ancient civilization? Does it prove that Antarctica was once inhabited? Is this evidence of a lost world preserved beneath the ice waiting to be discovered? The excitement is real, and it is entirely understandable because the image is genuinely striking. But here is the truth, and the truth, it turns out, is nearly as fascinating as the myth. Those pyramidal structures in Antarctica are real formations. They exist. You can photograph them and they will look, especially from certain angles and in certain lighting conditions, exactly like man-made pyramids. But they are not man-made. They are the result of a geological process called differential erosion, a process that has been shaping mountains in frozen environments for millions of years. Here's how it works. When a mountain is surrounded by glaciers, those glaciers act like slow, grinding tools, carving away at the rock from multiple directions simultaneously. Over vast spans of time, we are talking millions of years, this process can sculpt a mountain into a shape with multiple flat angled faces meeting at a central peak. Geologists have a specific term for this formation. They call it a horn, and the most famous example of a horn in the world is the Matterhorn in the Alps, a mountain so perfectly sculpted by glacial action that it looks, from certain angles, almost impossibly precise. The Antarctic formations that look like pyramids are horns. They are geological masterpieces created by the patient, grinding work of ice over geological timescales. They are real, they are remarkable, and they are entirely natural. This distinction matters enormously, not because we want to diminish anyone's sense of wonder, but because the truth is, if anything, more wondrous than the myth. A civilization that built pyramids in Antarctica would be extraordinary. But a geological process that can, over millions of years, sculpt a mountain into a shape indistinguishable from a human-built pyramid, that speaks to something even deeper, to the profound creative power of natural forces operating over timescales that utterly dwarf anything in human history. The mountain was being shaped before the first hominid ever stood upright on the plains of Africa. The ice was carving those faces before our species even existed. That is not less remarkable than an ancient civilization. That is more remarkable than almost anything we can imagine. The same principle applies to many of the other mysterious formations that appear in aerial and satellite photographs of polar regions. What looks like a doorway in a cliff face is most often a natural opening created by the differential weathering of rock. Some types of rock erode faster than others, and the result can be an opening that, especially when photographed from a particular angle or in low light, appears to have been deliberately shaped. What looks like the hull of a sunken ship, glimpsed through ice or in aerial imagery, is typically a rock formation, a ridge, or a shadow cast by the complex topography of a glaciated landscape. This is not to say that every strange formation has an immediate, obvious natural explanation. Sometimes the explanation takes time to find. Sometimes geologists need to travel to a site, examine it directly, take samples, and run analyses before they can say with confidence what they are looking at. But in the vast majority of cases, the explanation, when found, is natural and often more interesting than the supernatural alternative would have been. The doorway claim that forms part of the title of this exploration, a 220-year-old doorway found in Alaska, is a perfect example of this dynamic. The number itself is striking, not thousands of years old, which would suggest a pre-Columbian civilization, not millions of years old, which would be purely geological, 220 years. That specificity lends the claim a kind of false precision that makes it feel more credible than a vague claim of ancient origins. 220 years suggests that someone has done the analysis, dated the formation. It suggests science. But the reality of what was found, and what it tells us about the history of human presence in Alaska and the natural forces that shape stone and ice in extreme environments, is, as we will discover, genuinely fascinating in its own right. Alaska is a land of extraordinary extremes. It is a land where the landscape shifts from dense boreal forest to open tundra, to glaciated peaks, to volcanic islands within spans of distance that would feel modest anywhere else on Earth. It is a land where the permafrost, the layer of permanently frozen ground that underlies much of the terrain, preserves things with a fidelity that no other environment on Earth can match. And it is a land with a human history that stretches back at least 14,000 years, and possibly much longer, encompassing cultures of extraordinary sophistication and resilience that developed over millennia in one of the most challenging environments our species has ever inhabited. The notion of a doorway in Alaska, of a passage or opening in ancient stone or ice that might mark the site of something significant, resonates so powerfully because it touches on deep questions about who was here before the historical record begins, and what they built, and what traces of their presence might still survive in the frozen ground. These are legitimate